And our first speaker is Mitro Volin from Uppsala University, and he will speak about non-local geometry of beta algebras and monodromy bootstrap. So, thank you.
Hello. Yes, good. So hello, everyone. Yes. Yeah. So I'm going to speak about this, and these are the people who I'm working with. Great thanks to them. I announced what I'm planning to do about this program on the same conference 2015 in London. These pictures actually from that slides from that conference. These are not new slides. The story starts from realizing that integrable systems that we are working with, they have equations that are non-local equations. What do I mean by non-locality here? That we have the same function appearing in an equation which is evaluated in two different places of the complex plane. This is non-locality. And to make sense of the equation, we need to know how to connect the 2 points. If function is analytic, there is no problem. It's whatever path you choose for connecting, get the same result. But if there is a branch point, then making in 2 different ways, moving, give you 2 different things, and then this equation suddenly stops making sense. Because what do you mean by writing such an equation? Appearance of such branch catch is actually quite a severe thing, a severe constraint on what you can do. And many classical work on integrability from the beginning assume 3 options: rational, trigonometric, and elliptic. Like there is even some theorems, but these theorems actually hiddenly contain assumptions that the functions are single-valued functions. And there are quite many communities that work in this domain. Eli mentioned there are hyperelliptic cases. I'm very curious what they're actually doing there. What we know for sure that in a DCFT integrability, branch points are present. It was completely convincing after the time we realized what is the analytic structure of dressing factor, BAS dressing factor. Since then, it was clear that branch points are unavoidable. But exactly in this form, it became a part of the day life when we were studying Y system on mirror T-hook. This was not actually that much during conferences in 2009. People were showing picture of T-hook, which was nice. But I mean, those who work knew that there is a problem passing far away from mirror region. And there were some claims that Y system is dead and discussion about that. So for DCFT, it's reality. And I kind of try to say that instead of saying that it is reality which is problematic, let's embrace it and use to our advantage. So the idea of monodromy bootstrap is quite simple. We say, OK, we have branch point. We will even postulate their existence. And then we take our system, go around branch point, and require that something nice happens with our system. So star here means some symmetry transformation, which one we can choose and define different models. This is a very simple idea. So this is actually a crossing equation in reality, implemented in a quite strange way. Well, it's easy to say this phrase, but there are a lot of questions to ask how to implement the idea. And when you try, you soon realize that you're asking always the wrong questions, because system is not the one that you are used to. The goal of this talk to explain a framework of ideas which allows you to start asking correct questions about monodromy bootstrap for this situation. And this is what I really want to convince today. Before going into framework, I want to tell you that already in 2015 and before, there were two proofs of concept existing. First, of course, is IGST quantum spectral curve. In fact, in our paper, there is a section which people really use or ignore, or usually they ignore, because this the section doesn't help to compute any anomalous dimension. But in fact, it is about this idea written in a different way. And so we did not use this idea to derive this spectral curve. We used TBA, but this gave an inspiration. And then just mimicking this inspiration, it's possible to derive Hubbard. With all details, we did it only recently, but the equations themselves I already put in my talk on IGST 2015. So this is like baby version. The main difference appearance of function f, which is because the central charge is non-zero, and this is important. Without this you can't do Hubbard. I will speak about this later. So these are two inspirational examples telling that you're not crazy, things can work, and let's try to make them work in general. And this is the general goal of this program. Given a symmetry algebra, some Lie algebra G, apply monodromy bootstrap idea and get some spectral curves of a DCFT type. First big problem is really what is Q. We see here there are some Q systems around, whatever they are, but what is a Q system for given Lie algebra? And this is not something that is clear at all. And most of the talk today actually will spend on explaining, given Lie algebra, what is Q system, and we will do arbitrary Lie algebras, simple Lie algebras, in fact. And then, after I explain this, you will have good set of ideas, hopefully, and it will be much easier to explain how monodromy bootstrap work, and, well, there will be some more declarative statement about IGST CFT spectral curve conjecture. When you will do all this business, actually there are many spin-offs. These spin-offs about both rigorous and efficient improvement of studying variety of integrable systems, which not necessarily DCFT, like rational speed chains and so on. We have quite a few results there, which are quite interesting by their own sake. So this is my plan, and so let us start. We start by just discussing what I would mean by Q system. What do I want? The simplest thing to keep in mind is rational spin chain. Mathematically, it's some representation of Yangian algebra. So you do your transfer matrix, construct set of commuted quantities. We call this set of commuted quantities beta algebra. Some people call it Baxter algebra also. And you kind of often say that commuting quantities is landmark of integrability. But here is this funny part, that if your Hilbert space is finite dimensional, having commuting quantities gives you zero in knowledge. Why? Because look, you have just big matrix, okay? Imagine that this matrix has non-degenerate spectrum. The worst possible integrable model to have zero degeneracies, right? It exists as an integrable model, but so let's take this case, the spectrum is non-degenerate of this matrix. Then by just simply taking power of this matrix, you for sure generate all possible commuted quantities you can ever have. It's only when system is infinite, it's becoming a non-trivial task. So saying you have finite dimensional Hilbert space commuting quantities, you say nothing, it's always true. So integrability doesn't really lies in existence of commuting quantities when it's finite dimensional Hilbert spaces. Yes? And this is the next point I'm going to make. I also make it provocative for the reason, right? So it's not about commuting quantities themselves, but the fact that you can organize commuting operators into functions of spectral parameters. And this function of spectral parameter should satisfy quite non-trivial functional relation. And when actually you see this, then it's actually integrable, not before. And as Matthias mentioned, of course, it eventually can be equivalent to beta equations. So to see what I mean by this philosophy, SU2 spin chain with periodic but with diagonal twist in periodic boundary conditions, so just to make less degeneracy, And so M magnum sector, everything standard. And for this spin chain, we can construct two Baxter Q operators. So I actually have to cite here very many different groups present in this audience for how you can do this. And we have two of them, actually. I will call it red and yellow. During this talk, there will be a lot of red. There will be always red and yellow skews. So this is a typical example of red. This is a typical example of yellow. So this is polynomial GM modified by twist factor, and this is other polynomial modified by factor. So, so this is just some matrices which are polynomials in U, and their determinant should be equal to U to the power L. So we call it Vronsky and beta equations. So this is non-trivial functional relation. You see here shift plus I virtus, shift by minus I virtus is actually already non-local equation. I emphasize this, non-local equation already here. And I don't really focus on that this should be some function here. It can be any function. I focus on the fact that this here is identity matrix. So Q and Q, white and red and yellow Q are commuting matrices. But if you randomly choose commuting matrices, this type of expression will unlikely give you identity. Even more, suppose you fix Q somehow, and then you try to find yellow Q such that right-hand side is identity. And then again, you will fail unless zeros of this Q satisfy beta equations. So this is really non-trivial constraints, which is for me today will be really how I see integrability. It will be basically a definition. By doing, so I said about matrices. For the rest of the talk, I, however, will stick to eigenvalues. So I just wanted to make like allusion to the question that we want commuting quantities, but eventually it will be eigenvalues still. And we proceed, so you can think about them as eigenvalues in the following. Right, so there are two bonuses about doing this logic. So first, that there is actually rigorous statements about completeness for these systems. Those who try to solve beta equations know that they have problems. So this equation doesn't have problems. It always have correct number of solutions. This was proven by Mukhin, Tarasov, Varchenko 2009. And bonus number two, actually, if you have two Q functions, you can easily construct all the transfer matrices. So it's very compact formulation. So this is type of Q system, very simple one, which you want to do something similar for any simple Lie algebras. And this is what I mean by Q system. So because I will be very general, I want to slightly change notations. So I want to reabsorb this parameter inside Q functions. I do it by introducing dressing factor. So I say my polynomial time dressing factor should be another function that determinant is equal to 1. So dressing factor satisfies some crossing equations. It's not a crossing I would speak today about, but it's another type of crossing. Right, so I just redefinition. So I will not have explicitly any source terms like this. I will be hidden in the definition of Q functions. So it will be less number of functions to speak. Yes. This one, yes. I did it to speak less about details, yes. But everything goes without SSL, but just have to make more clauses, yes. No, it completely solves there as well. I just don't say about it. Its statement is fully fixed there as well. Right, so this first thing, and second thing I want to notice that this red and yellow functions actually organized in a vector. Well, it's two-dimensional vector, so you can guess that it's a transform induction of SU2, and we have SU2 spin chain, so kind of relation, but in four-dimensional system it's hard to guess if it's accident or not. But anyway, this is a vector, and you can compute transfer matrices by doing these nice wedges. So sorry, like this, with different shifts. If shifts is like this, equal to 1 is the same determinant as here. So, okay. So this is type of equations I want really to generalize, and this one. And before even going to real work, I want to tell you philosophy of the generalization. So Q system is really about quantum mechanics versus classical mechanics. So take an energy conservation. It can be written as a quadratic equation for P. You can do it in this form. It's clear you have permutation symmetry. It's called Galois group of this quadratic equation S2. Right? You can permute two Riemann sheets, and this is type of asymmetry in our world. When we do quantization, you have Schrödinger equation, and now it's really wave function who is the main character here. And there are, like here there are two solutions. There are also two solutions to this equation, but now it's quantum mechanics. You can do linear combination. It's called superposition. And symmetry is no longer S2, but GL2, which is Lie algebra already. But also in quantum mechanics, we always projective. We do not care about phases. So real symmetry is PGL2, whose Lie algebra is SL2. So this is quantum mechanics. In the integrable world, we also have higher order equations. We can consider Lax matrix, n by n Lax matrix, right? Classical spectral curve. Then symmetry will be Sn. And there are some way to quantize either honestly or philosophically. Anyway, this is, at least philosophically, it's Baxter equation, but there are examples when we can prove it. Again, this is the same story. There are n solutions. We can take any linear combination. So we don't care about normalization, so it's projective GLN, whose Lie algebra is SLN. So the whole point that when you quantize, your permutation group become Lie algebra. And general story is the following. Then you have some Cox-Star graph, well, Dynkin diagram for Lie algebra. Then it has actually two things, classical things, which is Weil group or Cox-Star group of this graph. So a system of reflection are associated to nodes. Simplest case is permutation. On the other hand, it's have associated Lie algebra, and building Q system is actually updating this group to something, to update something that transform induction of Weil group to something that transform induction of corresponding Lie algebra. This is really what happens when you build Q system. And now I will tell you, considering simply Lace case. Just a disclaimer, doing GLN is boring because that doesn't show you all the important features. You can easily miss the point when you do GLN. But anyway, I will tell you the point, so if you don't want to focus to GLN, you can do it in your head, and then I tell you, okay, this is the point. Okay. So I remind, we want something, so SL2 is a Dynkin diagram with one node. Associated to node, we have two Q functions, whose Wronskian is equal to 1. I have to introduce something what's called QQ bar system in the literature. It's the following thing. You have your favorite Dynkin diagram. To each node of Dynkin diagram, you associate one Q function, and which is called red Q function in this talk, and also one more Q function, which is called yellow. And you write what's called QQ bar system, which is Wronskian of red and yellow function at a given node of Dynkin diagram, equal to product of all Q functions at the node adjacent to your node. So here it will be, for instance, 3 neighbors, and they will be product of 3 Q functions. For the moment, yes. It's to start. Eventually, we'll come to non-simply laced. Now, for the young part of the audience who did not see this argument before, I will explain how this goes to beta equations. What you have to do, you have to take this equation shifted by I over 2. So this bracket means 1 in the, so plus means shift by I over 2. 2 in the bracket means shift by I, like twice by I over 2. This is also 2 here. It's not clear, but it's 2. So you shift this equation by I over 2, get this equation. I shift by minus I over 2, get these equations. And then you actually consider it as the zeros of red Q function. It becomes 0. And then the determinant becomes product of on diagonal. And then when you divide, this yellow function disappears. So you get this ratio. And this is a beta equation. This is how a QQ bar system is related to beta equation. Okay. Very good. So now we start to go to play mutation game. So I call it for this talk mutation game because it's very similar to cluster algebras. Like some of you know what is cluster algebra related to Y system, for instance. So it's not the same thing, but it's very similar logic though. Mutations are known by many different names, by many different groups. So it's people doing this all on top again, name it every time different name. So what is mutation game? So you take your favorite Dynkin diagram, write explicitly QQ bar system, and define mutation in the node SA, like somewhere here, as a following operation. You basically take, let's for instance here, mutation at node 2. So you take your Q function, red Q function, and replace it with the corresponding yellow Q function. But also, if you do this replacement, you have to update your QQ relation. So you see here we have Q2 in 3 places. So we have to make 3 places for replacement. And by doing this replacement, we actually modify 3 equations. When we modify 3 equations, this means that the role of yellow function should change. Because, of course, this Q1 bar will not say yellow Q1 bar, this one, yellow Q1, is not going to solve new equation. A new different function will solve this equation. So what will happen when you mutate function at given node, you also affect what would be called yellow function. It will generate new Q functions in this way eventually. So it's important to realize. And so this is one mutation step. And the game is to make mutation again and again and again and again and again and again until you reach some saturation point. Either you are tired or you exhausted all possibilities. There are 2 options. And this, if you're clever enough, you can exhaust those possibilities before you are tired. To become clever, we have to consider a classical case. Classical case is called character limit when Q function just a twist to power minus IU and times some number which I will be caring about. This is called character limit. In this case, all the transfer matrices become characters. It's exactly when quantum mechanics become a classical thing. In this case, if you will do mutation, first of all, Q function are replaced by Y. It's not Y function, it's just numbers or variables which do not depend on spectral parameter, which define your twist. And when you just solve this equation for in terms of Y, you see that Y has this transformation. And if you know a little bit of character theory, it's actually Weyl group action on just simple characters. So character is a trace of a group element, and you can take diagonal to group element, some number to the power of Cartan generator. And so if Weyl group will act on Cartan, it's exactly what will happen with your Ys. So this is like standard fact, and you just can refer to any textbook on the subject to know that all this beast will transform under action of normal Weyl group by in normal standard way that you absolutely are aware how it will go. And then you can ask the question, what will be orbit of this tuple of Ys? And the answer is nice. It's a number of elements of Weyl group. This means that Weyl group act freely. There is no Weyl reflection that stabilizes any tuple. It will always change until it exhausts the whole orbit of the Weyl group. This is good. And but more interesting question is if you focus on particular Y, like Y2 for instance, and you just record what possible values Y2 happens on the way of mutations, it will be less than the whole Weyl group. Much less, and you can ask how many. And the answer is also known. It will be length of the Weyl orbit of A's fundamental weight. So probably you know that Dynkin diagram for each node, there is a fundamental weight who makes some orbits, but also it has associated fundamental representation of Lie algebra. So I just give you 2 examples, like this Dynkin diagram for SL4. So, and here these numbers actually answer this question. So Y1 will achieve 4 different values on the Weyl orbits. Y2 will achieve 6, this is 4. So it's binomial coefficients, and probably you can, and also the dimension of corresponding representations. So in your own framework, you can probably understand why it's so. But here for SO8 is more interesting. So this is vector representation, it will be 8 guys, these 2 spinors, which also aids the reality. But here, we actually will have 24 from this Y, will be 24 different values of this Y. Y24, well, it's actually 8 choose 2 minus 4. So 8 choose 2 is anti-symmetrization of a vector. This is what this representation is. This node corresponds to adjoint representation, which is anti-symmetric vector representation. So this is 24, but Cartan elements are never in the Weyl orbit of raising and lowering operators. So raising and lowering operators can always mix up by Weyl transformations, but Cartan can't. And so the answer is here 24, not 24. But anyway, this is the answers, and this is the answer for mutation game on D series, for instance. And now, after we studied classical game, we are going to go to full quantum version of the game. Full quantum version of the game saying that now these Q functions are function spectral parameter, and mutation means actually solving this finite difference equation in some favorite way and replacing red function with corresponding solution. And here the fun starts because this is first order equation that hence any solution is solution of inhomogeneous equation, this inhomogeneous equation, plus any addition of a homogeneous solution. So alpha can be any number in reality. And even more, it can be a periodic function. But for today, I will speak only about its being number. Right, and so we have ambiguity what to do. There are two things to do. One option is to work hard and find a way to constrain the ambiguity. For instance, introduce back twists. Says now Q functions, let's say, Q functions will be some twist times another function of U. And yellow twist is different from red twist, so it's very different asymptotic. So by fixing pure asymptotic, you can fix your favorite solution. There are also other, even randomly ad hoc ways to fix your solutions. This is possible. And then there is quite a non-trivial statement which requires some work, not some, but serious work actually, to show that if you fix your solution by some tool, good tool of course, then you actually, even in this complicated functional case, you do exactly like in characters. It will be the same well orbit like in characters, and you reproduce what our friends call Hasse diagram. And so this is explicit realization of well orbit of characters. So you can open the paper, see the indices, and even understand what's happening with indices. Okay, so, by knowing that is how characters transform, we of course can do the same Hasse diagrams for any algebras immediately. Right, and because it's the same game, you will have exactly the same number for Q functions. But now, and this is something which we always were not willing to do, but recently realized it's another feature, but not a bug in the story. We actually will allow to get linear combination of homogeneous part freely. That means that every time we do mutation, we allow to add anything we want, and every time it will be something different, randomly. Just on the Mathematica, it's easy to do. And so let's see what happens in this case with mutation. So if you start from some red Q function, you have a linear combination of two guys. But if you do mutation again, actually it can be linear combination with any coefficient with only requirement that projectively these two numbers are not the same as alpha 1. Because I don't care about normalizations, I only make projective statements. It's like homogeneous coordinates in projective space. So ratio of alpha prime beta prime should be different from alpha. That's only requirement, otherwise it can be arbitrary. And so in particular, alpha prime beta prime can be alpha can be any, so alpha prime beta prime is completely unconstrained by the choice of red Q 2 steps before. So something different changes. So there is a good analogy for this. It's those who know for you Stokes phenomena. You see, have to think about red Q as small solution and yellow Q as a big solution. When you start with a solution which is smaller than a given Stokes sector, it's uniquely fixed. Then if you go to the next Stokes sector by crossing Stokes line, then solution become big, but it can have a small solution as addition, but its asymptotic is still under control. But if you can cross another Stokes sector, you're lost. It can be anything after that. This is standard story from Stokes phenomena and WQB analysis. And by the way, this is not only analogy. By ODIM, it's precise equivalence between what I'm doing and what is done in ODIM equivalent. And this is how we actually use things to prove statements. We do ODIM dual, do things there because there it can be done rigorously, and come back to get our results. Right, so then because these numbers are arbitrary, you can go on, and of course you will go forever, and asking how many answers you will get is meaningless, infinite, but you still notice that it will be always linear combination of two functions, only two. So can you ask what is linear span of, so you have some seed, red Q, and then you do mutation for eternity, and you can ask, okay, this is some functions, how many linearly independent functions are there? And the answer will be 2. So we replace number of elements on the orbit by dimension of linear span, which in this answer is 2. And so we play the game. And for your convenience, I give you more examples because there will be no numbers. More numbers is more convincing. So I took two SL-type Dynkin diagrams and two D-type Dynkin diagrams, and ask the question, okay, I take my Q function, do this mutation with possibility to add linear combinations. So I do superposition like a quantum mechanics, really. And ask myself, okay, what will be dimension of linear span? So for A-type Dynkin diagrams, the answer is exactly the same as of the orbit of corresponding character solution. So that's why I case is boring. You will not see the feature. But for these guys, this 24 becomes indeed 28. So the linear span will be bigger than the length of the corresponding Weyl orbit of a character. So Q function that you will get actually will span the whole adjoint representation, and this is actually true for any diagram. You can even compute it by Mathematica experimentally, which of course we do it originally, or you can eventually prove the statement. So here are the numbers of character orbits, and this is dimensions of corresponding representations. So this is antisymmetric, this is 3 times antisymmetrized. So the statement that Q functions are no longer Weyl orbit of characters, but they actually form corresponding representation of corresponding Lie algebra, and this is where update comes. So what we achieve, we replaced red Q functions, but a big column of functions. So you have a real big zoology of functions by now, like if you big to high algebras, exponentially many guys really. But what we achieved by this is that they form vectors that are in corresponding representation of the symmetry group, and we achieve covariance in description of beta algebra, which was not there before. It's covariant induction of symmetry group by now, very explicitly way. And after we did this, original QQ bar system will be replaced by statement from representation series. So here we have red and yellow guys, and this is actually first 2 components of this vector. And this Wronskian, but now this Wronskian becomes wedge of this vector, and this product of leading coefficient becomes tensor product of corresponding representations. Vector. So this equality is what replaces QQ bar system. By the way, this equation was first realized in this paper, and also here it was present. But they did exactly the opposite of what we did. They started from DAM. In DAM, it's more easy to understand why this is true. And then they say, oh, first component of this equation is this equation. Hey, we get QQ bar system, we get beta equations. We are happy because people really wanted to get beta equations out of their consideration. What I'm telling you now, no, you should not be happy to have beta equations. You should actually get covariant description instead. And this is very many functions and even more equations. Number of equations here is much more than number of functions. Actually, mutations close eventually to a finite linear span. So the fact that you can actually solve them is highly non-trivial. And the fact you can, and yet you can solve with all that function beyond functional freedom of your solution. So there are still as many in the non-fixed function by this equation as rank of your algebra. And so I perceive this, and eventually prove this by doing a representation series of, let's say, finite dimensional representation of affine algebra, and quantum affine is integrability. So kind of I speculate here, but stating that this equation is kind of like a Yang-Baxter equation on the level of beta algebra. Suppose if you do not know R matrix, you do not know all the stuff about Greenfield doubles and so on. For instance, in the DS 554, we do not know, right? After one loop, it's a big open question, like probably the main question, which is open. At least in my perspective. But nevertheless, you can replace Yang-Baxter equation. Let's say this is Yang-Baxter equation, if you wish, for beta algebra. A BGM is not, we do non-supersymmetric case for the moment. Okay, moreover, these equations are good, but we found more relations, much more relations, and we found geometric meaning of this. The fact that these Q functions describe something which is called fuse flag. So what it is? So by definition, flag, not fuse flag, by flag, is a homogeneous space of complexly group G by complex Borel subgroup. It's just a definition in mathematical literature. It has nice geometrical interpretation, but it's just a definition. And how we work with right here definition. So how we work with how we can parameterize homogeneous spaces? Well, in physics it's called order parameter in phase transitions. We take your Fourier objects that transform induction of G, and then it's also invariant induction of B. If you want to break symmetry from G to B, you find order parameter which is preserved by B but changes under G. And then, so if there is an object who has B stability group and transformed on G, orbit of this object under G exactly your homogeneous spans G quotient B. So let's do this for flux. So this, of course, it's clear that tensor product of these vectors will live in tensor product of a corresponding representation. So they live in big vector space. Highest weight vector in this big representation clearly annihilated by raising operators and only rescaled by Cartan. So projectively, up to normalization, this highest weight vector is invariant under action of B. Hence, the orbit, G orbit of this vector in this space projectively is precisely will be our G quotient B, will be our flux. And now rough claim that we are making that this very special vector in this very big space lives on the orbit of highest weight by action of G. This is a rough claim, and this claim is very non-empty already, because what we can show that Q functions which live here form not arbitrary vectors, but null vectors, light cone vectors. Only possible is to be light cone. It can be only null plane. This is null 3 plane, and these two guys should be pure spinors. Nothing else is possible in integrability. But it's not all. This was rough claim. The exact claim is that it's fuse flux, because I never spoke about spectral parameter here. But everybody depends on spectral parameter, and everybody non-locally, all equations are non-local. So this statement is actually true if you do small quantum shift of each spectral parameter. So the statement is the following, is that this tensor product with this very specific shift live on the orbit of some G orbit of highest weight vector if this vector P, P1, P2, PR, has this property. The difference of 2P is plus or minus 1 if they are adjacent Dynkin nodes. Moreover, this should be true for all choices of such vector P, not only for one, but for all. And the statement for all is actually equivalent to beta equation. So derivation of this fact is use of DAM. And remark to connection to mathematics, you hear the word opera, nobody knows what is opera. So I tell you, opera is this guy. Okay, so now you know what is opera. Okay. Find a difference opera. Okay. So I hope you got an idea of what is big Q system on fuse flux. It's some geometric object of this type, and it can be constructed after doing very many mutations, and it has have covariance and action of symmetry algebra. But as huge object, is it even useful? So very quickly about usefulness of this object. Right, this is a repetition. We actually had this equation. To make use of this, I actually have to recall that there is a dressing factor and come back to original equation. So the answer is, for instance, that analog of beta equation is this QQ system. This is Drinfeld polynomials now. It's equal to U to the power L for vector representation, 1 for all other nodes. It's simplest spin chain. So let's make such just interesting claims from mathematics. For the moment, it's proven only for a few cases. Otherwise, it will be conjectures. So QQ bar system is written here. It's original one. It's not all this green stuff which are generated. It's original one. Original QQ bar system has the right number of solutions for generic values of parameters. And also beta equations most likely has right number of solutions for generic value of parameters. Both of them actually fail for specific values. In both cases, you actually have to babysit them to get correct answers. What is improvement that this new covariant system conjecturally have the right number of solution always. So it will capture, for instance, all correct exceptional solution automatically, and this will be a rigorous statement. And then you can reformulate with this one thing. Another thing that you can do all this machinery to reformulate beta equations and concentrate them in one node of Dynkin diagram using these big vectors, which are not that big on the ends of Dynkin diagram. And for instance, you can get to Wronskian beta equation. Or for SO2N case, we got some interesting Wronskian type beta equation using pure spinors. And the statement, we for instance conjecture by extremely extensive check that this is always correct number of solution. And moreover, we can quickly generate thousands of solutions to beta equations by using these approaches. And of course, the most known for this audience is Hirota system. So the point that this is covariant, T function is invariant, And scalar product of two covariant vectors, this is A and this is A star, contra-gradient representation. This scalar product with appropriate shift generates a function which solves Hirota for any Dynkin diagram. And this is new, so Ferrando, Kazakov did it for D case, SO2N. We did also for SO2N, but also for E series, and I will show you now also for non-simply laced case. Okay, I will go very quickly to non-simply laced case without much of details, because we still have to do monodromy bootstrap. 5 minutes, wow, great. Yeah. But I started later, right? Huh? 15? 15 minutes, okay. Okay, non-simply laced case to very quickly. So in this case, first notice that Cartan matrix should be replaced by symmetric Cartan matrix. And this changes, so it's to Kostya question, this changes to some changes in this QQ bar system and change the mutation game rules. But you play the same game of mutation, and for instance, it lasts to SO7 case. And for the question, what span, linear span by Q function to get, you get these numbers, which completely different from dimension of corresponding representation of B3. So it's 12, 7, 13, 21, 28, no connection really. So what happens is that this number actually hiddenly representation of unfolded diagram A5 is binomial coefficients. So what you discover is that Q system is not representation of B3 any longer. So what is symmetry algebra? It's not also 7. For Q system with symmetry algebra, it will be SL6. But there is some folding connection. So there is some rules of the folding, which I will fix. But actually, we know the answer that it's not even simple folding. There is some folding using automorphisms. By the way, keep PV vary because it's what we're going to do in monodromy bootstrap. We also will have some automorphisms there. And so there is some rule, there is some interesting shift to spectral parameter. And the statement, this falls under representation theory, not even of A5, but twisted affine A5. And hindsight behind that original symmetry, well, you know the quantum integrability, Bell trillion quantum affine, not B3, but it's affinization and some stuff. And Langlands dual, whatever it is twisted affine. All right, so this kind of, you can guess it after you become clever enough, you can guess the answer anyway from the beginning. Right, and but also notice that this is 6-dimensional representation. It has nothing to do with 7-dimensional representation. So it's actually also 6-dimensional representation. When you fold this diagram, it's not B3, it's actually C3, which is symplectic. So just for fun, Q function on this node happens to be in representation of SP6. So transfer matrix in vector representation of SO7 is given by Q function in 6-dimensional representation of symplectic group, a completely different group. And this is a symplectic structure, it's anti-symmetric form now, not symmetric. So when you start from, so what we learned, so in general, when you start from symmetry in your system, to produce Q system, you have to do Langlands duality, and after that things change. So Q system can obey different symmetry, related by different symmetry compared to original spin chain. Okay, so this gives you an idea how to generate Q systems. Unfortunately, this idea has to be developed to get more interesting results, but at least you get a framework. And now I come back to simple cases, A series, G, but supersymmetric, and we are going to do monodromy bootstrap. And here I just really want to focus on the main idea. So in this equation, there is tilde and there is star. Tilde means analytic continuation. This will be next slide. And star means applying symmetry. What we learned about symmetries. So Q functions, this green big Q functions, that transform under symmetry group, which is reality Langlands dual to original symmetry group of the integrable model. And this group realized by matrix is actually I-periodic because it's finite difference equation. And also because everything was projective in quantum mechanics, we also have to do explicit rescaling. This is called in this business gauge transformations. So this is our symmetry that we are allowed to use. And also, of course, something like changing diagrams to the opposite diagram, something discrete, like Hasse, duality, swapping groups. So it's called out-automorphisms. So these are symmetries that you can do. So making your choice, well, this will give you a model. Actually, only choosing automorphism, auto-automorphism changes the model. Other symmetries are constrained by monodromy bootstrap already. And second is, what is analytic continuation? In Andrea talk, analytic continuation will be noted by gamma. So now I just tell you quickly, so if you think that it's a simple, no, it's not. Because all these Q functions have actually big ladders of branch points. So our system is non-local. It evaluated different points of peripheral parameter. So it cannot go around branch point. Because if this guy goes around this branch point, another guy will go around branch point. You destroy your system like you destroy Y system by trying to make it through. So analytic continuation in just stupid naive wave will not work. So the idea is that we have the symmetries, so this will not work. What we are going to do, we will use symmetries to all the time have absence of branch points while we proceed with analytic continuation. So we start with system which is analytic in the upper half plane. There is no branch points, and everything is good. Then we go here, staying away from the cuts. And when we are here, we can perform symmetry transformation to make system analytic in the lower half plane. Because cut on the left, we allow to use periodic functions, which we called omega, which is symmetry of our Q system, which have cuts also on the left. So we use omega to create no cuts in lower plane, and now in the lower plane, after symmetry transformation, we are good, and we go up in the middle. And now we use, so we go up in the middle, and now we use other functions, which is called mu. They have cut to be outside, otherwise periodic here, that again create our system, which is analytic in the up. So you make the full cycle, applying symmetries on the way, and require that this guy is related to the original guy by some way. And now we start to crank machinery. And if you look on this formula, something you realize explicitly that, you know, automorphism, it's quotient, it's inner, it's sum automorphism by inner. So in reality, you cannot just flip the Dynkin diagram, you also have to make a symmetry transformation. So when you flip it back and make symmetry transformation, you do not come to original point. So this procedure tells you that having branch cuts is actually, branch cut of square root type is probably not even possible, and usually it's not. And this was big revelation for us in this business, that actually this branch cut square root type is a luxury of a DS5. Generically, we don't expect it. Because of this procedure, it's already, you can see it. And so now the only thing you have to do, you have to tell what symmetry you want. Type option is considered this SU2/ diagram and says that this star means Hodge duality. This means that you flip this function to this function, then you get some equation. This is PMU system. It looks like follows. Whatever it is, but I just want to tell you one theorem. If one requires square root type condition, I want the branch point of square root type. I like a DS5. Then I cannot impose f squared equal to 1. By the way, I forgot to say, f squared equal to 1 is zero such condition, which would make from SL2/2 PSL2/2 case. And moreover, maybe should be antisymmetric. And I got a spectral curve like this. Only possible option with square root cuts. And this only possible quotient is called Hubbard model. We can derive TBA from here. We can derive Lipwood beta equations and Bizart version of them and compare with the result of this group. So this is derivation from a non-trivial bootstrap of Hubbard model. We can also say that star means do not make change, because monodromy involves a lot of interesting symmetry transformation. It's still non-trivial statement. And we get another model and conjecture that here, first of all, theorem, you cannot make it with square root cuts. It's just impossible. And if you want central charge equal to 0, then conjecture that it's actually spectral curve for DS2 CFT1. And finally, to get DS3 CFT2, we need two Q systems because it's two copies of SL2/2. By the way, there is a quiver describing PMU system here. And so what you do, analytic continuation actually swaps the two guys. So there are some equations, and the conjecture is when it's central charge equal to 1 case, then it's actually a spectral curve for DS3 CFT2. And Andrea will speak in detail about details of this curve. They also have derivation, different, and he will speak a lot about this. Interestingly enough, we also have type D model, which is because what you can do, you can map this to this model, and this model map to Hodge dual of this model. So this is actually automorphism of degree 4. So there is some fancy model, PMC, some sort of fancy model, I have no idea what it is physically, which has automorphism D4, and well, we do not know what it is. Okay, and so now come to conclusions. So the first conclusion is that we propose to extend normal Q functions, Baxter Q functions, whose zeros are beta roots of normal beta equations, to a big class of green Q vectors, really, who covariantly transform under symmetry Lagrange dual of original symmetry. And all the properties neatly of them are neatly formalized in geometric statements that they form a fuse flag, which is a geometric statement, but it's also non-local geometric statement. Fusion is because p's can be different, and it should be always true. Comment, very many different groups work on this in many corners of the world. I cannot possibly cite everybody, and I apologize for everyone who on the site. We have more than 200 citations in the paper. So this is a very small subset about who did Q system at least. All right. So for instance, this list doesn't contain anything about Q operators. It's only about this mutation game story. Right. So, and conclusion number 2, that now we have a good intuition about what is Q system, and we finally can start playing the game of applying monodromy bootstrap idea. I told you that it's non-trivial because of non-locality. Defining continuation is hard, but it's possible. And we finally got the first predictive statement. First predictive statement that we got a D3 CFT2 case conjecturally when it was not known in the literature before. So it's first time we do something before something else done by some other method. But now the hope that we can crank it for different algebras and make a DCFT integrability generic. It's not isolated point like it's now, like 3 cases or 4. But it can be like systematically for any algebra, for all the type of parameters. So it's like becoming its own class, like elliptic, trigonometric, on top of this also a DSCFT. So it will be like a big thing, and it could be interesting for different reasons. So for instance, what I described, it seems work for SLN/N. Well, we have to check still details, but preliminary it's still okay. So it will be something new. And future goal, of course, is PK. So Kolya, we're working on it. I did not finish with it. To fully say that everything is good and nice. Of course, D21 alpha is like holy grail to see that it really works, because nobody knows what is there. And if people, I know why QRL algebras are interesting, so people who know it as well, speak with me. We will have something to share. And finally, notice that with flux, it can be interesting because apparently there is non-finite dimensional representation of finite algebras as there. Okay. And finally, the very last slide, all the system is a universal algebra geometric structure which appears in whole big list of different groups. And we have a program about it in Simon Center. So if you're going to Santa Barbara, you can stop over. Right? If you don't go to Santa Barbara, you just go directly to us. And yeah. So you're welcome to come. And if you want to work on this, I have much more questions than capability to solve them physical. So if you want to work on it, please contact me and we can work together. Thank you for your attention.
So it's time for questions. Okay, first you.
So even if you didn't quite go into detail, I have a bit of a curiosity about the ADS3, which maybe is a bit also more general, because in the ADS3 case, there are massive and massless excitations. And if I look at the S matrix, I forget where I get this integrable model from. It seems that the S matrix bootstrap with fusion and crossing and so on, it closes just for the massive guys. So it seems that I could construct naively an integrable model just with the massive guys. And in terms of the sort of symmetries that I would have and representation, it would look very similar if I did, for instance, TBA. And my question is, if that is true, there should be some sort of ambiguity when you construct a quantum spectral curve just from PSU 1,1/2, essentially, to get the full model with the massless modes, or the model with only the massive, or maybe something in between with just something else that completes the model. What's your take on this?
Well, first answer, there is no fixed answer for massless nodes. But actually, by experience with Hubbard model, we see massless mode sourcing massive mode by fixing clever ansatz on zeros of function f that we have. And function f appear indirectly in a DS3CFT spectral curve. So this observation suggests, and this is current belief, which is not confirmed yet, that massless mode is very special zeros of the same Q functions. So there will be no need to add extra symmetries, extra Q functions node. It will be just there, just it's extra zeros which live on the cut. On the cut things are problematic. Because it's on the cut, it's periodized and become infinite number of zeros. And it's hard to treat, hard to make asymptotic, but eventually we hope that we will fix it. And well, then we will check if it's true. But for the moment, this is what we believe. There will be no need to extra sync. And also, I will be happy to do this because I have no idea how to do U1. U1 is the one which is so empty that I do not know what to ask about it.
Do you think that a model without massless mode would just not exist in the
No, I would say counter curve automatically has massless modes because you have to consider all possible solutions. And one of them will be massless modes. It's just hard to physically see the solution.
Hi. So the question is, you can generate equation for quantum spectral curve, but big mystery, at least for me, is always why the set of solution is a set of isolated points. So
Set of what?
Isolated points, right? So the spectral curve generates is non-empty and like non-continuous, but a set of isolated states.
If I discrete, you mean?
Sorry?
I don't get, what do you refer to isolated point? What do you mean by isolated points?
Like at the end of the day, the claim would be that this gives the spectrum of the theory, which is a discrete spectrum, right? So, but from the equations, you can't really count the number of degrees of freedom. In a sense, will it generate a line of solutions or like a plane of solutions or a collection of isolated points, you see?
No, but well, I also am not sure. Isolated points of series is just discrete set of solutions. I don't know.
So once you fix coupling, the size of the cut, you just get a discrete spectrum.
Yes.
So how to prove that in general? That's the question.
No, but you also can get TBA from here, so I don't know. I mean, so for instance, for Hubbard, you can get Libou equations, but also can get TBA equations. What will change?
Yeah, but TBA equation is defined up to undefined set of driving terms, right, which could also be continuous.
Right, so the statement is as usual. So Q system is set of all this Q system, including monoid bootstrap as well, is a set of functional relation. And monoid bootstrap fixes a little bit its analytic structure through a Hilbert problem. But what it does for you is, okay, it's not polynomial, it's not trigonometric polynomials, it's this modification. But then the logic is as usual. We have to produce, inside there is hidden source terms, and there are source terms. And source terms come from extra analytic structure requirements for your functions. And now you have to play the game. I want this source term, and this will reproduce that theory. Okay?
No, just for me, it's always a surprise. So whether there is one isolated non-solutions or a continuum of them. So you just have to hope that it works. If you have ideas how to prove it in general, that would be helpful. You know, to count number of solutions. You have set of equation. Now one should ask existence and uniqueness, basically.
Well, I mean, then I would do it like in a DS5. I go to the coupling, and there we almost have a proof that it's only that possible. I mean, but I'm not sure. It's a little bit. It's next level question, quite hard.
I have two little questions. Maybe you had something in your transparency, but very briefly about it. For A algebras, there are two useful notions, equations to solve for the spectrum of integral models. One is quite old, it's Baxter equation, yeah, which is very useful. And another thing which was newer was the Wronskian Wronskian beta equations, where you formulate in one single equation the whole nested problem. And in the algebras, in our work with Gunael and Ruben Frasek, we had this problem that we had Wronskian beta equation, but it was sort of, it was not clear whether it's overcomplete, undercomplete. There were more equations than...
this I can answer, right?
Yeah.
Because
and the second thing is about Baxter equation.
Yes.
Baxter equation is not finite, and that's why not very useful in these systems. So can you comment on it? Do you have some progress on it?
Yeah, right. So I flashed through this because it was, but yeah, I can tell you a little bit. So normal beta equations, like it's or QQ-bar systems, are distributed along okay, let me find it. Okay, here. So normal beta equations are distributed along Dynkin diagram, like have A is node of Dynkin diagram. To get to something which we would call Wronskian beta equation, we have to focus on the last node of Dynkin diagram. And in SLN case, there are two last possibilities, both of them quite equivalent. And this get normal Wronskian beta equations, okay? Which is nice. And so now the game to fix Wronskian beta equations, we can fix either on fermionic nodes or on vector nodes. I know the equation, so I will answer it fully. So for fermionic nodes, we found these equations, and we found conditions to make it complete. What you propose is over complete, and we know why. Okay, so basically, but I will explain what you propose. So what you propose roughly is the following. So let's take this equal to 1. It should be u to the power something here in reality, and let's use this projection property. The scalar product of vector is 0. So I think this is what you're proposing, and this you say, okay, this should be beta equations. Because let's say that this is a Q function in a vector representation. Scalar product is 1 is normal quantization condition, and projector phi 0 reduces number of functions to the normal one. So if you try to solve it, actually written here, can be used as version of beta equations. So if you try to solve it, you will get too many solutions, but you have to impose only one more constraint, is that v plus which v minus is divisible by u to the power L, which is not part of these equations. So you take many equations and change the constraint and conjecture that it will be complete in generic situation.
That's true.
This is answers?
Yes.
I can write you equation level. So, so what you did, you missed one kinematical constraint. It's not dynamical. You're basically computing for different representation of spin chain, which is bigger in size. If you add one more constraint, it will be correct representation of spin chain. And second, about Baxter. First of all, we thought a lot, we speak with you, and we thought a lot about Baxter. So what you want from Baxter is that it's linear equation whose solution is Q function, and now whose coefficients are invariant under action of Lagrange duals that are introduced. So if you require the coefficient invariant under Lagrange dual, you will, by action with this symmetry, you will, of course, generate all the big Q vector present here. So it's automatically, it doesn't matter how you try, it will be always that huge thing. And if you want these two things, you're doomed. But what is good about, but now if you don't want to write linear equation, but you want to make a generating function like ratio of two things like Koniba, like you did for super case, then it's more optimistic, but well, we can discuss in the break. But I told you why it will be problematic, just normal one. It will not exist because it doesn't satisfy the required symmetry of the system. No.
Thank you.
No.
So, okay, I think it's time. It's time for coffee break, and let's meet at 10:25.
the two talks, which will start now, we will try to make a conference photo. So before walking to the restaurant, please, we will go outside that direction, and we will wait in front of the building, and we would like to take the photo there. Okay? So please be there.
So our next speaker is Alessandro Sfondrini from Padova, and he will speak about mirror thermodynamic beta ansatz for ADS3 CFT2.
Thank you very much, and it's a great pleasure to be back in Budapest and to be back at IGST in person and to have the opportunity to give this talk. It's a particular pleasure because it's a topic that like Ellie and also Fernando were saying, you know, something that we were doing maybe a while ago. For me, it was something that I was doing my PhD, the spectral problem of ADS3. Then I let it sit for a while, and it was a great pleasure to come back to it together with Sergei Frolov. And I'm going to tell you a little bit about how we get to the mirror thermodynamic beta ansatz for ADS3 CFT2, which describes the finite volume spectrum of this theory. So the plan is first to review some basic things about ADS3 CFT2. Maybe most people here are familiar with ADS5, so I will try to highlight the differences. And then tell you something about the S matrix, and in particular the dressing factors that were a bit of a surprise in our work. And then I will tell you about the mirror model and how you use it to do the TBA. So let's start with a review of ADS3 CFT2. And I will focus on the most supersymmetric and nicest backgrounds. These have half as many supersymmetries as ADS5, 16 Killing spinors. And they're all of the form ADS3 cross S3 cross something else. Something else could be T4, K3, or another sphere S3 cross S1. And all these are supposed to be dual to some two-dimensional conformal field theory with n equal 4,4 supersymmetry. And these superconformal theories are largely unknown, except maybe at a very special point of the parameter space. So in this talk, I will talk about only the planar spectrum of ADS3 cross S3 cross T4, which is in a sense the simplest of all these. Even if it's simple, this background has a lot of parameters because there is less supersymmetry. In fact, it has 20 moduli. But it turns out that basically only two parameters matter if we're interested in the planar spectrum. This is the amount of B field that there is in the background and the overall tension of the string. And for these two parameters, we have a classically integrable family of nonlinear sigma model. And the hope is that the whole thing is quantum integrable, of course. So let me just give you a broad picture of how these two parameters enter. The tension, of course, appears very much like in ADS5. You go from weak to strong tension, and you go from a more stringy to a more Sugra regime. But the B field changes things a little bit. So the simplest case, maybe for this auditorium, would be the case with no B field because it's the most similar to ADS5. It's related to the D1, D5 system. There is very little known about the dual. And the tension is some continuous parameter, like the Toft coupling. And the spectrum is not known as much as it is known for ADS5, of course, but we know that it's very non-degenerate and very non-trivial, just like the spectrum of ADS5 at finite Toft coupling. And in principle, we can get it through TBA. The opposite side of this story is when you have the maximal amount of B field. So in this case, actually, you can describe the model as a Vesu-Minovite model with group SL2 as well as SU2 and supersymmetry and all bells and whistles. This is related to the system of fundamental string and NS5 branes. And here, there are some much clearer ideas about the dual, even if it's something that only now people are really starting to understand quite in detail. The other thing is that here the tension is quantized, is actually the parameter K, which is the level of the Vesu-Minovite model. And the spectrum is very different. It's similar to the spectrum of flat space strings. It's simple, you can write it in closed form, and it's actually highly degenerate. Of course, it's easiest to understand this as a worksheet CFT, but you can also do TBA if you are so inclined, and that's something that we did with Andrea Day a few years ago. And then in the middle, you have the generic case. The generic case has both the parameter H, which is continuous, and K, which is quantized, turned on.
And it's very complicated. There is very little that is known about it. It's a rather generic setup. You can get it from deforming, for instance, this side. But qualitatively is more similar to the case with no B field in the sense that the spectrum is very non-degenerate, it's very involved, it's very non-algebraic. So far, in this case, we know only the S matrix. Even the dressing factors we don't know. So in this talk, I'm going to focus on the case with no B field and tell you about quickly how we get to the worldsheet integrability, the S matrix, in some detail the dressing factors, and then how we go to the mirror model and the TBA. If you have questions at any time or objections, just shut up. Shout up or shut up. Well, you choose. That's a Freudian slip if you ever heard one. Okay. Now, first of all, the symmetries. The bosonic symmetry of ADS3 is SO2, the bosonic symmetry of S3 is SO4. And in fact, SO4 splits as SU2 across SU2, as you know very well, and so in fact does SO2, just with a different real form. And the way that you package these into a superisometry algebra is that one SU1, and one SU2 end up making one PSU1, 1/2, which has 8 real supersymmetry. And then the other two guys make another copy of PSU1, 1/2, and everything is factorized into copies, which is precisely related to the fact that the dual is an n = 4,4 theory with a left and a right supersymmetry algebra. This symmetry is not so important for the S matrix. The S matrix is computing light cone gauge, and the symmetry that is important here is what you get after gauge fixing. And you actually break half of the supersymmetries. You are left with 4 PSU1/1s, which make for 8 supercharges, and a bunch of central extensions, which I'm just going to write for you. So let's start from here. You have 2 Qs. Those live in one of the PSU1, 1/2. These are supersymmetry generators. And 2 S's. These are super conformal symmetries generators. And they just give you a central element, which is basically delta minus J for one of the 2 copies of PSU1, 1/2. Some positive definite object, which is like the left part of the Hamiltonian in the dual conformal field theory. And then you have exactly the same thing in the right, with Q bars, S bars, L bars, and J bars. It's actually useful to introduce different names for these central elements here. So I call the semisum of these 2 guys H, that would be the worldsheet Hamiltonian, is something which is positive definite. And the difference between the left and the right charges, left and the right T1 charges, that's some sort of combination of spins, and I call it M. And then just like in ADS5, there is a central extension, like Beiser's central extension. Here it comes around as something that couples the left and the right supercharges. That's very unnatural if you think of the CFT maybe, but it's very natural if you think of the central extension for the S matrix. Just like the central extension of ADS5 is not something that you would naively expect from the structure of the algebra on the face of it. There are 2 charges, C and C dagger. And if you want to study representations of this algebra, we just have to give the labels H, M, and C dagger, the eigenvalues of these various central charges. So indeed, let's study this representation. The particles are short, meaning supersymmetric unitary representations. So this means that they satisfy a shortening condition, which I wrote here. H square is related to M square and C dagger. And then there are some other conditions. C and C dagger are actually conjugated to each other, and M is quantized. And as I said before, H is actually positive semi-definite. Using this relation, you get the dispersion relation, which looks very much similar to the one of ADS5, where M in ADS5 would be the bound state number. Here, the funny thing is that M can be any integer, in particular, it can also be 0. And then you want to study the representation for the different values of M, like in ADS5. I don't want to do this in detail, but I just want to tell you that all these representations are actually 4-dimensional. So you start with a boson, and either you get 2 fermions and another boson, or you start with a fermion and you get 2 bosons and another fermion. It's a bit different from ADS5, where bound states are actually bigger and bigger. This is just something which is always the same dimension, and basically you're just changing this parameter M here. Okay, So what are these representations that are actually appearing and important in our model? These are all the possible short representations, but what are the ones that we want? So remember, this is the dispersion relation. M plays the role of the mass. P is, of course, the momentum. H was the tension. And we will distinguish particles that I call left. These are particles that have m equal +1 or bound states of m equal +1 particles that have +2, +3, and so on. Then I will have right particles that have m equals -1, and the bound states have -2, -3, and so on. And then I can have particles with m equals 0, and in fact there are two such representations. These are called massless because this dispersion does not have a mass cap anymore when m is equal to 0. And here I have to be a little bit more careful because the dispersion now does not have a mass cap and it's not analytic anymore. It's not analytic when around p is equal to 0. So it's actually important to distinguish the case in which you are on one branch or on the other branch of this dispersion relation. In particular, I will call chiral if I am on the one branch and antichiral if I am on the other branch. Okay? These are not relativistic massless excitations, of course. The velocity of these particles is not constant, it's not the speed of light, but is basically cos p over 2. But still, we have discussed and we have to be a little bit careful with it. Okay, so this is the particle content. And knowing this particle content, I can go and compute the S matrix. So how do I do this? Well, I pick a pair of irreducible representation of my choice, for instance, two left ones, and I compute the S matrix by requiring that the S matrix commutes with the various symmetries of the theory. Or maybe I take one left and one right, or one left and the massless, chiral or antichiral, or one right and one left. I do all the possibilities, and I get a bunch of blocks. Now, it's quite lucky because each block, up to an overall dressing factor, which is not fixed just by imposing commutation, can be determined uniquely. And it satisfies the Yang-Baxter equation just automatically. So the only game remains to fix this dressing factor that cannot be fixed just by commutation relation because linear equations always leave you an undetermined dressing factor, of course. It seems that we have an awful number of blocks and an awful number of dressing factors, but if you think a little bit about it, they are not all independent. There are things like unitarity, parity, and also symmetry between relabeling everything that I call left and everything that I call right, which are sort of arbitrary labels. And these reduce a little bit the number of independent dressing factors that you have. So at the end, you are quite lucky. You have to deal with quite a few dressing factors with respect to ADS5, but not too many. And let me just show you which ones you have. So you have two dressing factors for massive particles. And the only thing that matters is whether the particles have mass of the same type. Let me just talk about particles of mass equals 1 and -1. I will do bound states later. So the first one without the tilde is when the mass is both +1 or both -1. Doesn't matter which one. And the second one with the tilde is when they are opposite masses. Doesn't matter which one is +1 and which one is -1. Then there is one dressing factor where one particle is massless and the other one is massive. Doesn't matter whether it's +1 or -1. And of course, there is also another one where I exchange them, the one which I wrote in gray here, where you have first massive and then massless is related by unitarity to the other one. But sometimes it's useful to write nice equations to keep both of them, makes things more symmetric, so I just put it there. But only one is independent. And then there is one where both particles are massless, and here you just have to distinguish whether they have the same chirality or whether they have opposite chirality. So all in all, we have to fix these 5 dressing factors. How do we do this? By crossing. In order to discuss crossing, I need to tell you a little bit about Zukowski variables. It's more convenient to express the S matrix and the crossing equation in terms of these variables. They are very familiar for people that work on ADS5 because they are exactly the same as in ADS5. So this M is exactly the role of the bound state number in ADS5. And this is the relation with the momentum and the relation with the energy. Now, one slightly new feature is that you can also have massless particles. And these relations here become a little bit simpler because x plus and x minus are no longer independent. There is only one x, xp, which is x plus, let's say, and x minus is just the inverse of that. Another thing that you realize pretty quickly is that for massless particles, it makes sense to consider real momentum, but not so much to consider complex momenta, because you cannot really cook up bound states of massless particles. So x for real momentum is just, or rather x squared is e to the ip, so x lives on the circle, in particular on the upper half circle. And then you have to define what crossing is, and it's exactly the same thing as always. Crossing sends x plus to 1 over x plus, and x minus to 1 over x minus, and therefore also x to 1 over x. And by doing that, you can see easily that you flip the sign of the momentum and the sign of the energy as it should be. And a few years back, using this technology, we wrote down the crossing equation, which I'm going to just show you. It's not very important, the form, but I just wanted to show you more or less how they look like. So the two massive phases, they are related. The one with the tilde and the one without the tilde, they are related by crossing equations. And you get two crossing equations depending on whether you cross here the phase with the tilde or the other one. And these right-hand sides, they are whatever they are. Okay, don't waste too much time. They are not the same as in ADS5. They are not straightforwardly related to ADS5. But they are just what they are. Then you have the ones for mixed mass phases. They become actually quite simple when we write them in terms of this function f of x, y. And finally, we have the ones for massless particles, which also are just written simply in terms of this function f. Now, one thing that you might wonder is there some sense in which I can take the limit of the massive ones and get the massless ones? And that works with a caveat, because if I have this crossing equation where I'm crossing particle 1 here in the first line, I can take the second particle to be massless, and I would recover one of these equations here. But if I try to take the limit, some analytic continuation where the first particle is massless, I don't get anything like this, meaning that taking this limit and crossing are not computing operations. I should be careful about that. So now it's a matter of solving these equations. Let me tell you how this was done initially. The first intuition, which was based also on semi-classical calculation, perturbative calculation, was that for the massive guys, it should be a little bit like ADS5, and in particular, there should be a BES, Beiser-Tedeschi-Staudacher factor. So the idea was, let's remove this BES factor, and then we get some equation for a curly sigma here, which should be something simpler. It's still something that has a non-trivial monodromy, so still a non-trivial function, but should be some simpler thing. Actually, technical thing, it's easier to write in terms of the product and the difference, or rather the product and the ratio of these two functions. You get nicer equations this way. And indeed, once you subtract out this BS phase, you get a simple equation. You see that is again written in terms of this f for the sum. And for the difference, you also get something simple. I didn't want to spell it out, but you see that now it's not a crossing equation for the difference, it's actually a monodromy equation. Okay, you should be a little bit careful just because you took the ratio. I'm going to say ratio and difference in like completely interchangeable ways. Okay, what about the massless? For the massless, one nice thing is that there is another parameterization that you can introduce, which is a rapidity parameterization, where you relate x to this exponential, to the ratio of exponentials. Now, this is still a fundamental parameterization, meaning that this is not something relativistic, this energy. But crossing starts to look a little bit like crossing in a relativistic theory. It's just a shift of this rapidity variable. And what is more, the S matrix for the massless guys is of difference form when you use this parameterization. So you start thinking that maybe you can solve this in terms of some relativistic dressing factor. And in fact, up to a sign in the crossing equation, which was initially missed, one gets that the crossing equation is, well, looks very much like the one of Seingord. Okay, very well. Then the old, which turned out not to be correct, unfortunately, and I should apologize because I had a hand in it. The old proposal was more or less this. For the massive phase, we first put a BES phase, and then we put some bits and pieces, which are basically related to the Hernandez-Lopez phase, or anyway to some order 0 term in the BES expansion. For the massless and the mixed mass, we just use this order 0 Hernandez-Lopez-like phase. And in particular, This is justified also by the fact that you sort of recover the sine-Gordon phase and the difference form. This was sort of the reasoning. Now, when you try to use this to do TBA, you run into several problems. Well, one first thing that we noticed is that already when we made this proposal is that not everything matches with perturbation theory, but perturbation theory is super tricky here because there are infrared divergences all over the place. So maybe there you could say maybe perturbation theory might have some problems and it actually might very well have some issues due to infrared divergences. On the worksheet, near BMN expansion. So when I say perturbation theory, I mean one loop near BMN calculations on the worksheet of the string. There is no other, there is no way to do this perturbation theory from the dual in this model. The other thing is that it has strange analytic properties. When you try to come up with one mirror model, you struggle. This match with the sine-Gordon at a sign in the crossing equation will give you some strange eyes, which of course mess up your reality properties. And then the thing that really we should have realized earlier, some of the phases actually violate worksheet parity invariance. So especially this last thing is quite conclusive that something is wrong with these phases, so you should sort of chuck them out and start over. So if you start over, you can take a slightly different guiding principle, and the logic is that because there are loops, of course, in this theory. When we scatter massive particles, you have massless particles in the loops. And they are going to give you some sort of massless dynamics in the phase of massive particles. And vice versa, when you scatter massless particles, you will have massive particles in the loops. And you will see some remnant of massive dynamics in the loop. So try to treat everything on the same footing. In particular, if there is a BES factor in the massive phase, why shouldn't there be in the other phases? Now, of course, you have to work a little bit to define what the BES phase is when one of the particles is in the massless kinematics or both, but that's essentially just an analytic continuation. So it's a technical thing, it requires a bit of work, but it can be done. Okay. Now you have all curly sigmas. The other ingredient is to say, well, if these rapidity variables are very nice for the massless, why shouldn't we use them for the massive? In fact, these rapidity variables, they were called Q in the Beiser and Andes-Lopez paper, and they already appeared there. So we introduced them. They have a similarly simple crossing. It's actually not exactly the same. The sign is different, which gives some very subtle things when you start putting together massive and massless. And what you get is that the physical region for the Zukowski variables, which is the outside of the unit circle, is mapped to two nice strips on the gamma plane. Okay, so this is the new variables that we have, and crossing is a shift. And then using these ingredients, you get pretty nice equations. You see here the equation for the sum is written in terms of differences of, for instance, gamma 1 plus minus gamma 1 minus divided by 2, then gamma 1 plus minus gamma 2 plus divided by 2, gamma 1 plus minus gamma 2 minus divided by 2, and so on and so forth. All the various combination of pluses and minus. So it's not quite of difference form, but it's made out of blocks that are of difference forms. And this property remains also for this monodromy equation for the sigma minus. And it remains for the mixed mass, and it remains for the massless, where plus and minus are for the massive particles, and I put a little circle when one of the particles is massless. So this would be gamma plus 1 minus gamma 2 massless, for instance. And now you just need to try to solve these equations, and since they are quite simple, you can try to, for instance, find a solution which is given by some difference of gammas for each block, and that has the zeros and the poles that are predicted by the bound states. And I'm just going to give you the solution. I'm not going to tell you how we found it. So the solution for the sigma plus is given by some function that ensures that you have the right poles, and then the product of 4 of these functions phi. For the sigma minus is given by, again, some factor that is there to ensure that you have the right poles and zeros, and some product and ratio of this function phi hat. These functions are, for the phi, is exactly the sine-Gordon phase. So here I write it in terms of the derivative of the log of the phase, which is very simple. You can also have an infinite product representation for this phase. You can also have a dialog representation for this phase. There are many ways of writing it, depending on what you need it for. But this sort of emphasizes it's a pretty simple function. And this phi hat is some new function that we came up with, which solves this discontinuity equation and has the right analytic structure. You can determine it very easily. And you see it's not a far cry in terms of complexity from the sine-Gordon one. And this is pretty much all you need to solve these crossing equations under this assumption that you use this factorization into gammas. And by the very same functions, you can solve the mixed mass, and you can solve the massless. So now you have your complete S matrix with the complete phases. You see that everything is written pretty much in terms of this phi, this sine-Gordon function. For these massless guys, by the way, notice that the phase is not exactly the sine-Gordon one. There is this little thing which had to do with this I that I told you. You have to be a little bit careful here to impose that the phase is 0 where it needs to be 0, and then you see that you need to put such a factor. What do we do with this? Well, we can start thinking about the mirror model and then the mirror TBA. Questions so far? Yes? You mean this thing here? Yeah. So this is a bit different, but it's also because, so for one thing, this you also have to integrate, and you get branch cuts, so it depends on which region you are. But you see that in this thing here, you get ratios rather than products, so it's a little bit different structure also because of that. But you can expand in the near BMN and check whether it falls off in that expansion, the whole combination, and you get the correct thing. Yes?
Can you understand the bound state as single pose of the...
Yes, I was coming to that, but yes. So the question was whether I can use these phases for the fundamental, or S matrix and phases for the fundamental particle to essentially fuse and get bound states, and the answer is absolutely yes, and I'll comment on that in a moment. Okay. Mirror model, and I apologize to the many experts in the room. I will say just a few words. So the basic idea is that we want to trade finite volume for finite temperature of a mirror model, and we want to do a double Wick rotation that exchange worldsheet time with worldsheet space to achieve this goal. So what I will do is that I will indicate with a tilde all the mirror model quantities. For instance, H tilde is the mirror model energy, and P tilde is the mirror model momentum. And the strategy is exactly like the one that was followed, say, in ADS5. Just like in ADS5, the dispersion relation of the mirror model is very different, so it's a very different theory, there's no question about it. But it can be obtained, just like in ADS5, from analytic continuation of the string model. So you can get this by analytically continuing the original model in a suitable way, which for the massive modes is actually the same as in ADS5. So for the massive modes, before the physical region was outside the unit circle, and these were the strips. In the mirror theory, the physical region is below the real line. And these are the strips in the gamma tilde plane, which you see are shifted. Just one reminder, what it means to be real is a different thing in the string theory and in the mirror theory. In the string theory, reality is x plus conjugated to x minus. You see immediately from this picture that that cannot be the case in the mirror theory. In fact, x tilde plus should be equal to 1 over x tilde minus. And also here we had gamma plus conjugated to gamma minus. Here we have that gamma plus should be conjugated to gamma minus up to a shift of I pi. So the reality conditions are different, as they very well should be. For massless is even simpler, because massless essentially can only have real values, so they live on a line. And as I said before, in the string region, they live on this upper half circle. It was e to the IP over 2, essentially. And that's the real line on the gamma plane. And in the mirror kinematics, you go on this segment here, which is shifted by I pi over 2. And then the orange line is the anti-string or cross region. So analytic continuation means going from this circle down to the line, or from this line up to I pi over 2. And of course, I'm not telling you how to do this because I'm not telling you where are the branch cuts of these functions and so on, but it's a technical thing. It's not a conceptual thing. It's quite a bit of work, but it's technical. So by using all this, what we can show is that we have a new proposal for the phases, and it satisfies all the good properties in the string theory by construction, crossing, unitarity, parity, and so on. It allows us to construct bound states in the string theory by fusion, indeed. And it can also be unambiguously continued to the mirror region. The phases that you get in the mirror region, they satisfy all the good properties that you want. And in particular, they satisfy unitarity in the mirror region, which is quite non-trivial because before we said the phase has a bit which is an S matrix element, maybe some rational function of the Zukowski variables. Then another bit which is the BS phase. Then another bit which is the sine-Gordon thing. And each of them, by construction, they were unitary by themselves. That's not true at all in the mirror region. After analytic continuation, the BS phase is not unitary. But the non-unitary bits of one part gets cancelled by the other. Like the sine-Gordon gives a contribution that cancels the part that comes from the mixed mass, the BS phase, and so on and so forth. And in the end, it is unitary as it should be. So that we also regard as a sanity check of the whole construction. And finally, we can also do fusion in the mirror theory to get the bound states of the mirror theory, and that also works. So now we have our mirror theory with bound states and all, and we can do the TBA, which is what I will do next, unless there are questions. So again, just a sketch. What's the idea here? We take the mirror beta equations, we take very large volume, and we try to identify what beta strings we can have. And in this theory, the beta strings are extremely simple, actually, because we can have bound state of left particles with left particles. We call them Q particles. Q is the number of constituents. Bound states of right and right particles. We call them Q bar particles. Then we have two types of massless particles and two types of auxiliary roots. And that's it. There are no strings where you put together a bunch of auxiliary roots with a bunch of other things, like, for instance, you have in ADS5 or in many other integrable models. So it's pretty straightforward. And then the fused equations for the mirror model, they look like this. This would be the equation for a Q particle with number QA excitations in the constituents. And you see that you have an e to the IP. Then you scatter it with other Q particles here. That's the first term. You scatter it with Q bar particles. You scatter it with two types of massless particles that you have in your theory. And you scatter it with two types of auxiliary roots. Those are your equations. And then there is more of the same. A Q bar particle, again, you scatter it with Q bars, with Qs, with two types of massless, with two types of auxiliary. Then you have the massless, same story. And then finally, you have the equation for the auxiliary root, which is scattered with all the main roots. The auxiliary S matrix happens to be 1 in this model. OK. Then you can turn the machine of the TBA once you have this, and you can get canonical TBA equation basically by opening a textbook and studying it. Again, I apologize to the experts in the audience, but just a few words. The idea is that we take thermodynamic limit. Instead of having roots, we have densities of roots. Instead of having products, we have sums and then integrals for this density of roots. We impose that we have a finite temperature, and we impose that we have equilibrium, that the free energy of this mirror model is constant. And then we get some equation for the root densities, which give you the mirror free energy or equivalent to the ground state energy of the model. So these are the ground state TBA equation that I'm talking about. Now, I'm going to express right away these equations, not in terms of densities or pseudo energies, but in terms of Y functions. And because of what I said, we will have Y functions for the Q particles, Y functions for the Q bar particles, two types of Y functions for the massless particles, two types of Y functions for the auxiliary particles, which are also split in plus and minus, exactly like in ADS5, essentially depending on which side of the cut they fall on. So let me just flash now or discuss even a little bit how this equation look like. And I will actually not give you the canonical equations because they basically follow the structure that you saw before. I will give you the form that you find when you already start to simplify a little bit the equations and a little bit more structure starts to emerge. First of all, let me remind you that the actual ground state energy comes from the contribution of the energy here. Sorry, the energy here is given by the contribution of all the Q particles, Q bar particles, as well as the massless ones. They carry some energy, they are not auxiliary. And then we have very simple equations. You can simplify them to this basically canonical form for the Q and Q bar particles, where you have that the Q particle couples to the Q minus 1 and to the Q plus 1, and this is given by the standard Cauchy kernel S that people will be very familiar with. And you can see immediately that by acting with some inverse kernel, you can write a Y system equation type for these guys for Q greater than 2. For Q equals to 1, well, here you have a similar thing. You have that Y1 couples to Y2, and it couples also to the two auxiliary Y particles here, the Y minuses and the Y pluses. But then you also have another term here, which I put in some function f1, which depends on various Y functions. And this term here is not really important if you want to find the form of the Y system, but it will be important if you want to study discontinuity relation and do a very careful analysis. But again, as far as writing the form of the Y system, this actually looks quite nice. So this is where the good news stop, or maybe this is where the good news start, because now we get to some interesting things that start looking a bit different from ADS5. No, f is just some combination of the other Y functions that I'm not going to tell you what it is because it's just bulky, but it's on the paper. It's not just a source term. It involves essentially a bunch of other Y functions. It's a bit like in ADS5 for the particle number 1 equation. But it's a thing that only contributes to the discontinuity and not to the form of the Y system. Come again? It's like for? I don't hear. We discussed it, sorry. Yes, I think so, yeah. So I wanted to spend a little bit of time here because you see that now you have these two massless modes with these Y functions. And this equation here is something that we couldn't immediately simplify and looks a little bit more tricky to simplify indeed. By the way, I put some e to the I mu's all over the place just because the ground state energy is a bit trivial. You might want to break some supersymmetry to get something less trivial. That's not, you can think that these e to the I mu's are 1. But essentially here we start to see something new that does not immediately look like something that you can put into some universal Y system form. And then again you have equations for the Y plus and Y minus that are all in all not too dissimilar from ADS5. So this is the stand of this derivation. It's a derivation that only used basically standard text-to approach. There was a string hypothesis, but there was some study that we didn't find any other solutions. So it was pretty straightforward. There was as little guesswork as we could went into this. So what are the conclusions of this? Well, the first conclusion is that we have the mirror TBA equations, and we try to be as careful as possible not to put any assumptions. So this should be something that we are quite confident on and that you can use to check other proposals. In principle, you can just go ahead and compute the spectrum, maybe numerically, maybe analytically in some limit, but you can start doing this contour deformation trick. You can start considering some particular state, and you can start computing how the energy looks like, maybe numerically, for instance. The other interesting piece of evidence, or piece of information, is that we had to change quite drastically the proposal for the dressing factors. And the new proposal has really some quite non-trivial interaction between massive and massless modes. So the dynamics of the scattering of massless modes, it has a BES phase. The BES is a phase that knows about massive things, it knows about double poles, it knows about having a lot of cuts inside the unit circle and so on and so forth. And you cannot do without, we think. And the other thing is that you could probably take a model where you just say, I just have the massless modes, or I just have the massive modes. Maybe you have to change the dressing factor at that point, and that could very well be some self-consistent integrable model of which you can run the TBA machine and you can start computing things. That model will probably be something else. It maybe is related to some other string theory, maybe it's not even a string theory. But the crucial ingredient in order to get a string theory is to have both massive and massless and make them talk. What about outlook? Well, first of all, one can look at those TBA equations, say, well, you didn't simplify them enough. I want to find a Y system with discontinuity relations. And you take them, you study them, you work hard, and you get a nice Y system with discontinuity relations. And then maybe you get relation for the T functions. And then maybe you rederive the quantum spectral curve as it was done in ADS5 and ADS4, starting from the TBA. And then, like maybe that could be a way to have very good control on what you're doing. The other thing is that maybe you're just happy with the TBA, you just can use it to compute things. The question becomes, what do you compare with? This is the D1, D5 system. It's not the point where you have a Vesuminov-Witten construction. So it's not completely clear what you should use as a dual CFT, for instance, to compare. Of course, you can always do semi-classical or near BMN computation on the worldsheet of the string. But if you want to compare with the small tension of the string, then it's a bit trickier. We did have one proposal a few years back for a non-local Lagrangian that might describe this point of the modular space of the string. So it might be very much worth revisiting it and see if there is some match with that proposal and what you get from TBA. That would be quite interesting indeed, because that's really something where there is no other way to do the calculation currently. Something which is extremely interesting is this mixed flux integrability, which is quite wild. I just want to give this very nice formula for the dispersion relation. And you see that together with the usual sine square term, you also have a linear term. And that gives you very, very funky analytic properties. That's why essentially so far we don't really know what the phases are, and therefore we cannot run the machinery and get the mirror TBA. But it would be very interesting, first of all, because nobody knows how to do it, so integrability can really shine there, I think. And the other thing is that if you understand this, then maybe you can very carefully approach this limit where this k, the Vesuminov-Witten level, is something. And then you take the h, which is the Ramon-Ramon flux, to be small, and you approach the point where you can do calculation with CFT and where you can use either the Vesuminov-Witten model or the RNS strings or this hybrid formalism to deform a bit away from the CFT worksheet, the local worksheet CFT. And you can have another way, very robust way to compare and to extend the CFT machinery. And maybe you can even go and see how the integrability structure reduces to the CFT one in this case where you get essentially a chiral theory on the worksheet. So this would be all very interesting. So I think that there is a lot of work to do, and I think it is exciting times for ADS3. Thank you very much.
It's time for questions.
Thanks for the talk. Just about your comment that let's like drop massless modes, drop other modes, but why wouldn't you do the same in n=4, consider just SU2 sector, and we know if you, okay, classically is everything is fine, is integrable model, but if you now run your machinery, as you said, you will
sorry,
get garbage.
I didn't quite get just about my comment of what?
About considering separately massless massive, and getting like different types of results, different types of models. So you can just, in n=4, you can't restrict to a particular sector. You know that in the mirror model, all types of particles will contribute. If you restrict yourself in the physical, doesn't mean that in the mirror they will not contribute.
So the difference with ADS5 here is that from the point of view of the S-matrix bootstrap, if I put one massive mode with mass 1, I have to have one with mass -1 for crossing, and I have to have all the bound states. But I don't see anything at the level of the S-matrix bootstrap that tells me that I have to put massless modes. Now in ADS5, if I put, let's say, something in the SL2 sector, then I say, oh, but then I have SU2/2 or PSU2,2/4 symmetry that tells me that I should complete this to some other multiplet, and then I have to put the bound states, and then you get everything immediately. Here, essentially, the massless modes, they live in different representations, not only of the SU1/1 that you have in LightCon gauge, but they really come from different PSU1,1/2 square multiplets, in a sense. They correspond really to acting with some other generator which is not part of PSU1,1/2. So that's what makes it different. And it's also the reason why you have all these other models, like when you have ADS3 cross S3 cross K3 or S3S1, or even non-critical ADS3 cross S3 string. So I think that's quite a different here.
In formulating the mirror TBA,
yes,
you have to formulate first the string hypothesis. So I was wondering, how did you search for a complex solution of the beta ansatz? Yeah.
So we looked for, well, okay, this is already the fuse, guys. We looked for complex string solutions, and we couldn't find any that satisfied essentially the correct reality condition for the mirror model. And in fact, even in the string model, you don't have anything except for these left-left bound states and right-right bound states. So this was, of course, some. I mean, it's very hard unless you do a very extensive numerical study to be absolutely sure of this. So, and indeed, it's a string hypothesis, not a string theorem, if you want. But we were, I think, quite careful, and this fits with all that we knew. But if somebody does this study and comes up with some complicated solution with the complex configuration of roots and auxiliary roots, yeah, we would have to revise this. But I think we are quite confident.
Yeah, but did you do any numerical studies?
So we did a little bit also in the past. We also looked a little bit at this, but not extensively, I should say. Yeah, not extensively.
Thank you.
So I have a question about the physical beta equations, not mirror, asymptotic. So what happens when h goes to 0?
So
what do you get? A spin chain, something not local? What is the weak coupling of
it's a bit mysterious. Let me try to find a good equation, because the first thing that you notice, you can see it from this equation. Well, let's just forget about kappa. You put this k to 0, okay? And you will see that at small h, massive and massless excitation, they contribute a different order. Like that's the first sign that something is different. And when you only have massive at weak coupling, we think that we have some spin chain. That's this paper that I was referencing on the conformal field theory of the Higgs branch. But we never really managed to construct some sort of spin chain when you also look for the massless excitations. Now, I will say something that I'm not entirely sure of, but some of the things that Ellie was telling us about these n=2 theories, they don't look too dissimilar to what we would have in a spin chain of this type. The reason being that when you start from this construction of the D1, D5 system, you also end up with bifundamental fields, and you can decide how to integrate them out, and it should be quite interesting, I think, to revisit what we did several years ago based on what Ellie has been telling us. But I think it's a difficult question, and I don't have a straight answer, unfortunately. Certainly some non-locality is there. That's a basic bet.
So can you comment on Y system? So you wrote TBA equations, but it's very hard to realize their structure. So can you comment, it's just like what type of T-hook, where something could
I'm
I mean,
afraid
kind of some graphics to understand what's going on.
So I would have loved to put an IGST hook picture on this thing, but I didn't because I don't know. I only know that there are two wings here that you can see. They basically just look lines, like lines. But then essentially I don't know what happens in the middle because of this equation here. So I don't know how to reconcile this with I don't know how to simplify this equation, and I don't know how to get it into the form of a Y system and to give you an IGST hook. So it's a question that should be addressed, and I think it's an interesting question, and to my mind is the first step towards really understanding then how you get to the quantum spectral curve.
Actually, what is the meaning of mu of alpha in the second line?
This mu?
Yes.
Yeah, so this is, I just wanted to complicate my life a little bit, and I put a twist in order to make the model non-supersymmetric, because since we are just doing the ground state energy, there is nothing to compute if you are in the supersymmetric model. So this is some twist of the... So we didn't actually, so we wrote the equations, but we didn't do the calculation yet. But in principle, you should see that this gives you the twisted ground state energy for the values of mu, and then it should go back to 0 once you put mu equals 0.
Okay, thank you. So, very last.
Okay, could you comment maybe on the comparison of the new dressing phases to string theory? You mentioned to perturbative S matrix.
Yeah, unfortunately, even that comparison is not so favorable, I must say. It matches with, so I should say the calculations again are just from the string worksheet. And it matches with 3-level, that's fair enough, near BMN 3-level expansion. It matches with the near flat space expansion at one loop, but it doesn't match with the near BMN calculations at one loop that Sundin and Wolf did around 2014 to 2016. There are several discrepancies, but there are some subtleties in how those calculations are made, because there is an issue with having a UV regulator and an IR regulator in this theory. The massless modes actually become relativistic in the near BMN limit, and they should be also regulated. So we argue, or we believe also, that it should be possible to repeat more carefully the near BMN calculation and maybe get agreement, but as it stands, we don't have agreement with those results, even if those results are to some extent even self-contradictory, in the sense that even the final result is dependent on how the limits is taken.
Yeah, thanks. So maybe another way to test it could be to compare to some semi-classical state, which is protected from wrapping corrections, like folded string. There is a chance it may not feel
there was some work by, well, Arkady, and I think also yourself and Ben. So I was talking to Ben, it would be very much worth revisiting that calculation. Because if you remember, there was some mistake in one of the original calculations that was never really revisited. So yeah, it would be very much worth looking into it, I believe.
Yeah, so in some cases you cannot really compare because the standard solutions like circular string, they are full of wrappings, but for folded string it might be possible.
Okay.
Yeah, so I just wanted to follow up on Kostya's question about the spin chain and your answer to that. So I guess Alessandro Torielli and we got very disillusioned about finding a spin chain once this very nice Sine-Gordon picture emerged, sort of, or modified, Sine-Gordon-like behavior for the massless modes. When the S matrix and the dressing factors come out in difference form. So it seems like it may be more likely that it's a sort of field theory that sits there. I should say it's kind of curious. One thing, I don't know, Ale will correct me if I'm wrong, but I think we never really understood exactly what kind of Sine-Gordon theory it was. It's very similar to n=2 Sine-Gordon, but not quite. So that's a sort of challenge for people in the community. There's an S matrix, there's a dressing factor. What's the field theory? It isn't n=2 Sine-Gordon, it's very similar.
Ah, sure.
But if I could also make like a more general point, I mean, I think it seems the modification of the dressing factor is actually fairly small. once you write it in some set of similar variables. Maybe on there I will comment more. But it makes comparisons to Arkadis and Fedor's and others' calculations a little bit tricky as well. That's another point that's a little bit tricky. So it's funny, isn't it? The dual CFT2 is beyond mysterious, but it seems that also the semi-classical string is a bit mysterious.
Maybe just to comment on the comments. So about the dressing factors, I agree that once you know what they are, you say, oh, of course. It's very simple. It's just a small change. But once we were staring at the old ones, especially when you want to do fusion and fusion is not working, when you go to analytic continuation and that's not working, you say, what the hell is going on? I mean, you start thinking all sorts of things. The other thing that I wanted to say is that so there was this study of this massless sector only TBA from which to which you were referring, but I think that should be revisited because precisely things mix. And also I should say that in that particular paper where you do the TBA, I think you didn't do quite the mirror TBA, but the direct TBA, which I'm not quite sure that might be the exact thing to do, but it might be that, like the massless sector of this TBA equation is not exactly the same thing as taking the TBA equation for massless modes only. So I guess that's maybe a little bit of my point, that it's better to take the whole thing and then find the solution for the massless modes than say, let me start from the massless modes only, because you might end up fooling yourself. And if I'm allowed 1 second, I just wanted to a shameless plug of this Young Researcher School and Workshop that will be taking place in Nordita. It will actually be about integrability on the string worksheet. So it's very relevant to this talk and to most of our conference. And there is still time to apply, and I encourage everybody to apply. I will be sending a reminder just in a moment. You should get, everybody that is subscribed to this mailing, you should get it. And for students, I should say that we also have very generous support from Nordita, the University of Padova, Gatis Plus, Royal Society, and Science Foundation Ireland. So there is some support for students that want to come and maybe have limited funds. So please look into it, and you can discuss with your supervisor, or you can ask me. Thank you very much.
Speaker is Andrea Cavaglia from University of Turin, and he will speak about quantum spectral curve for ADS3 CFT2.
Okay, it's on, perfect. Okay, thank you very much. I would like to start by, sorry? Should I make the screen bigger? Is it not full screen? Thank you. So I'll start by thanking the organizers for getting us all together in this very nice conference and giving me the opportunity to speak. So I will talk about a proposal for a quantum spectral curve for this ADS3 CFT2 duality. And so this is a proposal that we made in work together with Kolea, Bogdan, and Alessandro. And also exactly at the same time, the same proposal was made by Simon and Dima. And of course, we should test it extensively. But I will discuss about the preliminary evidence that we have that it may be correct, and also about the logic of how we obtained it, that in this case we didn't derive it from TBA, but we tried a sort of bootstrap type approach to find the different types of quantum spectral curves. And maybe this approach could be useful to derive it for further models. So, and I want to say my talk will be very much inspired by ongoing works and discussions with all these very nice people, and also ongoing work which also involves Paul. And yeah, I will say more about this later. So, yeah, so the duality we're studying is one of the first holographic setups to be introduced. So on one side we have a string theory on this ADS3 cross S3 cross T4 background with purely Ramon-Ramon flux. And the dual side, as Alessandro said, is quite mysterious. So abstractly, this is defined in string theory by considering the theory that lives on the D1, D5 system of branes. And this theory is a sort of superconformal QCD in 2 dimensions. But to have the dual CFT, which should flow to the IR. So contrary to ABGM and n equals 4 superior Mills theory, this theory is not conformal. And in the IR, we find some mysterious, strongly coupled interacting CFT that we would like to study. And so there are not many techniques available. In particular, worldsheet CFT techniques in this case are extremely hard to use. Contrary to the case of pure NS flux that was recently essentially solved using this type of techniques. So the best bet to study this theory is integrability. So there is a lot of evidence that together with other ADS3 CFT2 dualities that this one has the same type of integrability on the worldsheet that we know in n equals 4 and ABGM theory. And so we're in the same conceptual framework, but with this significant new feature and complication, that's the presence of massless modes in the worldsheet theory. So our proposal is for the quantum spectral curve that we should give the solution for the full planar spectrum at finite coupling, where by coupling, essentially, I mean alpha prime here. But I'll call it just a Toft coupling. So this would be the third example of quantum spectral curve arising in this field. So we had one for n equals 4, one for ABGM. And so roughly, a way to describe it is that the quantum spectral curve is a sort of problem, a complex analysis problem, which defines some set of Q functions. So they, in particular, they will have some branch points, which is where the Toft coupling enters the game in the position of the branch points. And there are functions of a parameter called the spectral parameter. And the idea is that this problem will have a discrete set of solutions. Each solution corresponds to a state in the spectrum, and from this set of Q functions in this solution, we can extract the scaling dimension of the state. So it was observed and experienced in this previous case that this mathematical structure is quite rigid. For example, it was possible to find a variation by tweaking it a bit that describes the cusp anomalous dimension in n equals 4, the spectrum on a cusp Wilson line. And this is a bit of an inspiration for our work, because also in this case, this result was not found directly by deriving it from TBA, but just taking some information from TBA. But besides, we might be interested to see what types of quantum spectral curves can exist, but I want to emphasize that so it's something that is hugely useful in practice. So we can say, I think that in n equals 4 and ABGM, we can now answer almost any question on the spectrum. So almost because it's very hard to ask questions about like density of states or the behavior for asymptotically large quantum numbers, but any question that we can ask by studying a spectrum state by state can essentially be answered with arbitrary detail. So this is just an example that some applications, well, we can solve the equations numerically, and essentially there are methods to solve them with essentially arbitrary precision. And this is just, for example, one can plot the spectrum, and this is an example of the spectrum on a Wilson line in n equals 4. And there are very nice and powerful methods to solve them analytically in various limits, such as at weak Toft coupling. And so I plan to have this comment on what sort of numbers can appear. And so the quantum spectral curve gives very precise structural predictions. For example, in n equals 4, there should be only, in this weak coupling expansion, multiple Riemann zeta values. In ABGM, multiple Riemann zeta values with alternating signs. And I don't have concrete things to say today about IGST, but I will say this quantum spectral curve looks more complicated, so it looks likely that these would be more complicated numbers. But of course, connecting to the comment that was made yesterday, we should look if there is some tension with prediction from Feynman integrals, we should see how this is resolved. But so assuming the quantum spectral curve is correct, it's passed many tests, it gives very powerful and deep predictions. Sorry? Yeah, that's like an experimental finding, right? I think like this is the theorem that this is a class, an experimental finding, it's an even more restricted class. And then, okay, just as an extra motivation, there are recent directions where the quantum spectral curve is connected to computation beyond the spectrum, trying to solve a non-trivial correlation functions in a planar limit. And so we heard yesterday about this very nice new proposal of combining the hexagons with the exact spectral equations to compute OP coefficients. There is also this idea that so far it's much less developed, but there is evidence from various corners that Q functions are themselves building blocks to build correlation functions through separation of variables. And also there is this recent approach of trying to take spectral data, use them as an input in the conformal bootstrap. And this gives already some very accurate predictions for some OP coefficients of short operators. And you can see more about this in a poster by Julius. Okay, so, but now with this motivation, let me come to IGST. And so there are two possible ways. So there is a systematic way that was described by Alessandro already. And so it's in a way, it's the proper way to derive the quantum spectral curve would be to, as was done in the previous cases. So it's this very well-established idea that first we understand the integrable model on a very large worldsheet, which is a limit of large quantum numbers. In this large worldsheet, we understand the dynamics with the dispersion relation and the worldsheet S metrics. And then we make this worldsheet periodic. Then the spectrum is described by asymptotic beta ansatz. And then the thermodynamic beta ansatz is a way to make this volume finally finite. And so here is where we are now in IGST, as Alessandro described. And then there should be some quite complicated chain of simplifications that leads us from these integral equations of the TBA to functional relations and the quantum spectral curve. So what we tried in this work is to fix the quantum spectral curve from self-consistency requirement. And these two types of assumptions and input, which are assumptions about, so the input about the symmetry of the system and assumptions about analyticity of the Q functions. I will describe these more. But what I want to say is that, so we use essentially almost no input from the microscopic realization of the system. In particular, we don't use input about the worldsheet S metrics. And a bit like reverting the logic, we can reproduce at the end the worldsheet S metrics. I will say, concretely, I will talk about the massive S metrics and use this as a cross-check. And while the S-metric bootstrap approach in principle suffers from this ambiguity of CDD factors, which are an ambiguity that's at the beginning of this approach. So here we'll see that the quantum spectral curve has a prediction about what should be the right CDD factor. So and I will describe how we match this most recent proposal for the dressing phases. So what are these? So these are two types of assumptions. So the symmetry from the input from the symmetry, so it's a super conformal group of symmetries of the duality. This should become a global symmetry of the integrable system. And this should go in a totally model-independent way into the form of these functional relations satisfied by the Q functions, which are called the Q system. So I apologize, I forgot to put references here. But so we heard about Q systems in Dima's talk, and in particular for some algebras and superalgebras, it's completely understood what should be this structure, in particular for the A-type ones, such as was the case of ADS5. In ADS4, some QQ relations were reconstructed a posteriori. So ADS3 is so it's in the same class as ADS5. So in a way, it's two copies of a smaller rank version of ADS5. So from the point of the Q system, it's all completely understood. The hard part is talking about analyticity. So what are our assumptions? There is a very natural one, is that the charges of the system should appear in the asymptotics at large values of the spectral parameter of these Q functions. This essentially comes from the fact that this quantum spectral curve should match what is called the classical spectral curve, which is the mathematical structure that describes the classical solutions of the equations of motion of the string in a classical limit. And then to say the other assumption with the slogan is that these Q functions should have no singularities. The only singularities that are allowed are sort of kinematical singularities that don't depend on the states, but only on the definition of the model. And of course, so here, what are the rules? While we can essentially derive the rules for spin chains or the fishnet model for models which are as hard as this, or like nonlinear sigma models, we don't know the rules a priori. So what we did in practice, so based on the fact that these analytic properties were similar in ADS5 and ADS4, we'll essentially try to be as close as possible to these two previous cases. So essentially what we try to do, it's an assumption of minimality. We are trying to build two small copies of ADS5 and make them talk in some way. So if there is a model that satisfies these minimal assumptions, it should be this model because it's the one that at the level of the S metric is most closely related to the previous one. So now I'll say concretely more in detail what are our assumptions. But I want to make a comment that we do not input any special feature that is related to the massless modes. So of course, this is a very special feature of this model that was absent before. But we think there was, mathematically, we didn't see any natural place where this information should go. And so our working assumption is that they are present in this curve that we propose, and they should be somehow an emergent feature that will appear when we go towards this large volume limit. Okay, so here, let me just show what are these functional relations coming entirely from symmetry. So the symmetry tells us that the number of Q functions should be 16 plus 16 associated to these two copies of the algebra. And I will denote one copy with a dot on the indices and the other one without dot. And for each copy, we have some Q functions that satisfy relations such as those shown here. So the details are not important, but this plus and minus denotes just some shifts in the spectral parameters. and the indices are fused in a certain way. And we make another assumption that essentially the ones that are at the extremes of this fusion of Q functions should be 1. So you can see this as another assumption of minimality. So in principle, this could be where there could be some wiggle room in the construction, but we think, at the moment, we think that this does the job. And so a feature of these relations is that, as already was described by Dima, they imply beta equations. But these, so here, these Q functions are not polynomials. They will be complicated functions. So these are abstract beta equations. So whenever one functions have zeros, on these zeros, there are these types of relations, which can be derived in a simple way. For example, from this QQ relation, if you sit at the 0 of Q1, you get 0 on the right-hand side, and you see that this ratio should be 1. So this exact equation should match the asymptotic beta ansatz when we take this appropriate large volume limit. And we'll see that this happens. So now let me say concretely what are our assumptions about analyticity. And these come literally from translating what we know about IGS5. So from this expected correspondence with the classical spectral curve, we can say that some Q functions in a classical limit parameterize motion on ADS3 or on S3. And it was noticed that associated to these two types of functions, which are roughly, we're talking about the ones at the extremes of the Dynkin diagram. So in this case, there will be half of the Q functions. So these Q functions should have, on some Riemann sheets, some very simple analytic structure with only one cut. But these two types of functions have two cuts of different types. So the ones associated to the compact part of target space have a short cut, and the ones associated to the non-compact part have a long cut. And the positions of the cut is parameterized by the Toft coupling through some parameter h. So I will not specify what is h, but it should be a function of the Toft coupling. Okay, and now I'm ready to show you what is the proposal is. So the point is that between these two types of axioms about symmetry and analyticity, there is some tension. And essentially, we propose a simple way to resolve this tension. And I want to show you the proposal just with some pictures, essentially. So it's all contained in this slide. So one can derive some more equations from here, but this is just to show that it's a very minimal proposal, which ensures the compatibility of these two types of axioms. One can also axiomatize it more like Dima and Simon did, and in their case, given some precise set of rules, they could do a classification, and they found as one of the cases in this classification of possibilities the same proposal that we make. So the idea of this tension is that once we say that some of the Q functions, the one I labeled as P, should have a shortcut, then this QQ relation will try to essentially replicate this structure. And so the QQ relation then will predict that the other Q function should have an infinite ladder of cuts. And we can actually have two bases. One, if we say that we start applying the QQ relation in the upper half plane, we find an infinite ladder of cuts going down. And these are denoted with this arrow going down. Or another basis, if we start applying QQ relations here, we'll find an infinite ladder of cuts going up. But this should be compatible with this idea that on some Riemann sheet, they should have these long cuts. And the way to make it compatible is we propose we should glue these sheets together, which forces us to say what happens when we go inside the cut. So, sorry. The idea is we go inside this cut, and we come back on another sheet. But in this gluing of sheets, we also exchange these two wings of the system. So this is the only way that these two wings talk to each other. Otherwise, they would be completely disconnected. So in equations, this is written like this, where gamma denotes the analytic continuation as shown inside the cut, and this G, it's a matrix which should be a matrix of constants, not to change this analytic structure. And okay, we know a bit more about the structure of these G's. We think they are off-diagonal matrices, but okay, it's not so important. Yeah, so in pictures, essentially that's it. So now I want to describe some features of this new construction and why it's actually different from the previous cases. And this has to do with this Riemann surface where the Q functions live. So also in the other cases, it was very complicated. So we've seen there are infinitely many branch points, and also there are infinitely many Riemann sheets. So the current understanding in all of these cases is that if you go inside any cut, you get to a new sheet, and there are never cycles. So the new feature is about the nature of the branch points. So to discuss this, let me show some equations. So these are all equations that can be derived from this previous, from what I showed in pictures, essentially. So this equation is an equation that glues together Q functions with these ladders of cuts in two different directions. So there's two different bases. There is also an equation through which you can glue together Q functions with the ladder of cuts all in the same direction. And this now is not through a constant matrix, but through this matrix called omega, which is a periodic matrix. So it can be constructed explicitly out of Q functions, essentially. One can also derive what happens if we go inside the branch point of omega. It's given by this equation. And if we stare at it, it tells us that there is some special combination, which I denoted as U, which is a matrix where the cut on the real axis is absent. So it will have all the other cuts, but not on the real axis. And if we exchange the role of the two wings, I can define in the same way some matrix U dot. So now I can use these to study what happens if I go around the cut many times. So if I go around the cut of Q once, so this brings me to a Q on the other wing related by U. If I go twice, I find U, and then for the second time, I find the U dot. And if I go around n times, I get, in general, this product. And so what, in ADS5, there will be some algebraic relations in the system that essentially tell you that these cuts are quadratic. So this chain stops after two times. But here there are no such constraints. And so what we expect is that the monodromy is infinite around any branch point. In fact, if we try to force quadratic nature of the cuts, we found, as was shown by Simon and Dima, that this collapses the system. It will collapse these two algebras to just one, and this will become essentially the Hubbard model. So, okay, so this is a feature that we did not input, that these cuts are no longer quadratic. We didn't expect it, and in fact, at the beginning, we were really reluctant to accept it. It's also a feature that makes solving the equations much harder than previous cases. But we think it's a signature of the presence of massless modes in the system. So this is one way where this new feature appears. So we need to learn how to make friends with it. And what I want to describe is now trying to do something with these new equations. So I will describe this large volume solution and how this allows to reproduce the worldsheet S matrix in the massive sector. And at the end describes some preliminary numerics. So here it will be preliminary results. Don't expect still a plot as nice as the one at the beginning, but it will be evidence that this system has non-trivial solutions and that the equations can work. We have some, well, some heuristics. You can think that massless, well, this is really extremely heuristic, but massless modes are, normally we have these cuts periodized by this shift, which is related to the mass. And if you take a massless limits, heuristically you can imagine a ladder of cuts that collapses, and you get a superposition of many quadratic cuts that create some more complicated cuts. Yeah, another way of thinking is just that we know there is something strange in this system, which are these massless modes, and this is also something strange. Okay, so sorry, how much time do I still have? 18 or 18? 18, okay, thank you. All right, so so we would like to describe this large volume limit, but one word of caution is that it doesn't work in the same way that we are used to in ADS5 and ADS4. So this limit is defined by taking very large value of a charge on the sphere, which represents the volume, with delta scaling in the same way, and keeping the coupling fixed. And normally we're used to the idea that this is described by the ABA up to exponentially small corrections. So here, because there are massless modes, we can have virtual massless particles correcting the result. So the ABA is supposed to describe just a tiny region, and at 1/j already we need the contribution from wrapping. But so we will see that formally it still works to take this limit at the level of the QSC, and we will reproduce this massive, this ABA in the sector with no massless particles in the direct channel. We have some ideas about how to see the emergence also of the massless equations, but in this case, I think we understand this less, and the limit is a bit more singular, so I will not discuss this today. Okay, so the idea of how to take this limit is that worked in the other cases, is that in this limit, some Q functions will become small or large. And we can read which ones become small or large by looking at how the charges enter into their asymptotics. So once we assume that some are small, they will drop out of these QQ relations. And this implies some simplifications, where essentially we find some discontinuity equations that are exactly solvable. So in this limit, we can find explicitly what are the Q functions. And little by little in these solutions, we see that some building blocks appears, which turn out to be S matrix elements. And plugging this exact solution inside these exact beta equations that I showed before, one reproduces the ABA. So this is the logic. And to present what happens, so I want to describe a bit more the new non-trivial part, which is related to addressing phases. So I'll start a bit midway, because the beginning of this derivation would be exactly the same as in ADS5. So with the same type of argument, one can fix some of the Q functions in this limit. So in here, I'll just show what one finds. So in this solution, these Q functions are parametrized by the value of their zeros on their first Riemann sheet. So these are kind of parameters in the solution, and eventually they will play the role of beta roots. And there are also some functions that appear in the solution, which, such as this one, which essentially in their belly they contain already the dressing phase of ADS5, the Beiserted and Staudacher dressing phase. So this appears pretty quickly. One comment I want to make is that there are some proportionality factors here. So in this way, to solve it, it's a bit hard to fix them because some Q functions, in the end, we compute them by solving this type of equations, which come from QQ relations. So we'll have something for the ratio, and then we need to solve it knowing the analytic properties of Q. So it's a bit hard to find these factors, and I will just carry them around because they will play some role later. We think there is a way to fix them, but just we didn't compute them precisely. So, okay, so up to this point, everything was like in ADS5. The new thing is when we try to use this equation for going inside the cut. So, I mean, it's not, we would do this also in ADS5, but here it would be different. So this is, the first one is one of the exact equations that we have for going inside the cut. And now in this ABA limit, this piece that appears is something that was shown on the previous slides, something that we already know. And it becomes a relation between these two Q functions. So let's make an ansatz for them. So here I'm showing a very generic ansatz. And it's very generic because here I'm stripping some explicit factors just for convenience, but I'm putting here some functions A and A dot, which I assume to be completely general. The only thing that we know from the quantum spectral curve is that they should be functions with constant asymptotics at infinity and with only one shortcut on the first Riemann sheet, and no zeros. So this is one shortcut because this one appears in P functions. These are the one with the one shortcut. And through the Q system, this other one will also appear in a P function in the other wing. So it has to have the same properties. So now if we use this first equation, you get these two relations here. So the second one comes from a similar argument for the other wing. So we get these two relations for these functions. So, okay, we can look at them and we immediately realize that these imply that the cut of these A and A dot functions cannot be quadratic. So far in the other functions, all the cuts were kind of standard quadratic ones. And it cannot be because, well, otherwise we could derive the second equation for the from the first, just by undoing this continuation in the other direction. But this is not compatible with the form of the right-hand sides of the equation. So we see the cut cannot be quadratic in this case. And, but okay, so we can solve these functions. So to find a precise solution, I need also to know what's the proportionality factor. Because everything else is a product over these roots, let me assume also that the proportionality factor takes the form of a product over the roots. And with this assumption, we can find, well, let's just carry these constants with us for a moment. So the solution can be written as a product where a building block has this function sigma 1 and sigma tilde 1. And they should satisfy these two relations here. So now it's not difficult to verify that these two relations imply the crossing equations that Alessandro showed if we define some dressing phases through these type of ratios. And this is valid for any value of these C1 and C2 functions, which are functions of this second spectator variable, which doesn't go inside the cut, and they come from these constants up here. So let's take a moment to recap what was done. So we're finding these solutions in a large volume limit, and we find a solution that is parameterized by these roots and by this function sigma 1 and sigma tilde 1. Once we plug these into the exact beta equations, we reproduce the ABA in the massive sector, where the role of the exact dressing phases is played by these ratios. And so now, so I just showed that these functions will satisfy crossing, but we should solve the equations and see what solutions we get. And let's look at, for example, at the ratio of these dressing phases, which is the one that was different in the new proposal as compared to the old one. So for the ratio, if I define it as rho, and it satisfies this equation, where here I'm still carrying around this k of v, which depends on these constants that essentially so far we've been lazy and we have not really computed. So we can solve these equations. So it's not hard to see that with the assumptions on analyticity coming from the QC, there is only one solution. Because so we want a solution with only one cut, no zeros, constant asymptotics, and it's given through Cauchy kernel in this form. And there is a term that also depends on this k of v. And so from this, if we reconstruct these dressing phases, we find this solution. And now if we think that this should really be an S matrix, an S matrix should satisfy Brady unitarity. And this is like a trick, cheating a bit to fix what is k of v. So there is only one choice for k of v, which will guarantee Brady unitarity. Or in other words, it will guarantee crossing in the two variables, not just the first one. And if we plug this value, we find this prediction for these dressing phases, which agrees with this most recent proposal. And okay, so one comment is that in principle, k of v is computable, but even if we look at it as an ambiguity, it's not the same as a CDD ambiguity, because here it would be a choice between having an object that is not an S matrix at all, but if it is a good S matrix, it has to be this one, which Alessandro proposed. Okay, so now I want to describe, tell you a bit about some work that so far so good, but we need to do the hard work and try to solve the equations. And this is work we are doing with Simon, Kolya, and Paul. And so this is surprisingly hard in this case because of this new feature of the non-quadratic cut. So I will to tell you a bit about why the previous methods cannot be applied straightforwardly. So in a nutshell, the idea of a previous method to solve the quantum spectral curve was to first find a solution of the Q system in terms of some parameters. And then we impose these gluing relations, which involve us going to the cut and looking what happens on both sides. And imposing this equation will fix these parameters to some discrete set of solutions. And the parametrization that was extremely useful, both in the finite coupling method, but also it's essentially underlies the weak coupling method, is this parametrization is a Lorentz series in the Joukowsky variables for the P functions. And this was very useful because it allows you to cover this cut very precisely. So this is a parametrization that will converge on the full first sheet and on part of the second sheet as well. But now, because these cuts are non-quadratic, they are not resolved by these Joukowsky variables, so this particular parametrization will crash and it will not allow us to look in detail at the first cut. So we need to develop new methods, and this is what we are doing. I just want to show some preliminary findings. So the findings is that we have good evidence, and we find that these equations are not just empty mathematical equations, but they really have solutions. We find evidence of discrete solutions, and for example, this is an example of a plot of a scaling dimension for a state which, well, it has the same quantum numbers as the state defined in the ABA in this way. And in the region which we covered, we can do some fits at coupling with good precision already. I want to say this is, so it's still work in progress because there are still challenges. It seems quite harder than in previous cases to go towards strong coupling. So maybe we don't have the optimal method yet, and we're working on it. But it seems encouraging. And with the ability to do numerics, in principle, we can think of do some tests and check if the states with massless roots are here or not. So to conclude, we have a concrete proposal for this quantum spectral curve in this case, and we should of course test it more and to be fully confident. At the moment, it doesn't look impossible that it already covers everything, including the massless modes. And of course, it would be nice to derive it from TBA. That would make us fully confident. And preliminarily, the numerics seems encouraging. Once we had it, in principle, we could try to test conjectures for what is the dual CFT. So there are some conjectures, they look very abstract, but in principle, if one can find a way to do computations with these proposals, one can try to do some tests. And of course, it would be interesting to use this, of course, to explore the properties of this CFT, the physical properties. And for this, it would be really nice to develop in parallel conformal bootstrap approach. So we've seen that these two, so integrability and conformal bootstrap can give quite good results when working together. I think there isn't much developed in trying to bootstrap the CFT in the way of conformal bootstrap, and I think this would be very interesting to develop. And then, of course, if this works, we can ask about other models. So this ADS3 world should have a lot of different theories, and it's almost sure that in the other cases we will need more drastic changes of the analytic properties. It would be nice to know, to learn what are the rules, what are the possibilities, what's the minimal information we need to know about a model to understand what should be the analytic properties of the Q functions. Well, another question that's still open is what is this coupling that parameterizes the position of the branch points in terms of the physical parameters of the theory. This should be some dressed coupling like in ABGM theory, where it was fixed, so it's a challenge to fix it in this theory as well. It could be interesting to look at what survives of the QSC in this NS point, which is essentially solved. And maybe this could be useful to look at formalisms for correlation functions. And another world which would be interesting to explore is sigma models based on ADS2, which also are integrable. Okay, thank you very much for listening.
Questions?
Thank you. Thanks, very nice construction. Can you go to the one of the very first transparencies, I'm sorry, where you have the gluing rules?
The gluing, the colored one, like this one?
Yes, yes, here. So you construct here these gluing rules through the matrices G, AB, etc. as far as I remember, in quantum spectral curve for n equals 4 Young-Mills, you have a simpler formulation of these rules. You simply have complex conjugate, just for Q's with long cut. You simply complex conjugate, say, Q2, and you get Q4 with some coefficient maybe. This is essentially the only rule which you need. Here, why do you need to do this more complicated matrix? Do you need it really? Can you formulate like just simple?
Yes. Well, we think this matrix is it's exactly off diagonal, so it depends on actually only one parameter. So it will be 0 alpha 1 over alpha
but
0.
It's just complex conjugate.
Okay, yeah. In the case of real coupling, these different arrows are just complex conjugate.
But so it's as simple as for n equals 4.
Yes, yes. But in principle, you might want to explore taking the coupling or the spin complex. And in this case, to define them, you need to look at the Q system and solve it from 2 different directions. But so if you lose reality in some way, you need this more general one. Otherwise, it's the complex conjugate.
And the second question is a bit philosophical. I'm sorry, maybe you will have no answer on it. But we have now a few systems, like a few quantum spectral curves for at least 3 of them. And there is this more or less general way how to construct them. You build the Hasse diagram. You impose a couple of functions equal to 1, and then you pick up the nearest neighbors to these functions on Hasse diagram and fix some asymptotics and analytic properties, and that is everything. What breaks if you take other groups? I mean, did you think about it? Once I was asked by Sergio Ferrara on one talk, but can you use this construction to find other theories, other supersymmetric Young-Mills theories? What will break?
It could, well, so I don't know, it could be that we find more nonlinear sigma models in this way that are integrable, and that would be the dream, that it's a way to classify, although, yeah, I think we don't, I mean, we can decide the rules and try to play by these rules. Maybe we don't know yet if we want to find some specific class of models with what rules we should take.
Or we understand that these 3 cases are unique and we have nothing else. Yes.
It could be. Yeah, of course. It could be that you write some equations, but then they're empty, and numerically you don't find solution.
Thank you.
Thank you for the very nice talk. So I wanted to ask you a bit the dressing factor. So if you could come back to the slide where you were discussing this. Yeah. So in the paper where you originally proposed the quantum spectral curve, you were saying that you would reproduce all the dressing factors. So now, just to clarify, is this the same quantum spectral curve as that paper? Or so it was just that claim was not quite correct?
Yeah, the claim was not quite, in the sense that in that paper we were happy with reproducing the crossing equations, essentially, and then we kind of trusted the previous proposal for the solution in saying we reproduce it, but we didn't actually solve the equations. Then.
And now, if we can go back to the slide where you have the solution, so basically you have this discontinuity or this monodromy equation.
Sorry.
The one, yeah, that one, right? Yeah. And basically you are saying that this equation has a unique solution once you make certain assumptions on the poles and the discontinuities, but I guess that's always true, right? I mean, the point is, are these assumptions, I mean, are you absolutely sure that there is no wiggle room in these assumptions? Because even from the S matrix, if I say, oh, there are no poles in the physical strip and the fall-off conditions are so and so and there are no branch cuts, then I will be able to find a certain solution, right, of a discontinuity equation. So how much wiggle room do you have for this solution?
For the solution, I mean, following from the rules I set at the beginning, there is no more room, no more wiggle room here. Then in our construction, we could ask, what could we deform? Maybe one point is this thing. But yeah, I don't see much. Well, of course, we could say the position of the casts it's different, or they should have some other singularities. But.
And one last quick question. So there are, in this model, not only there are massless modes, but there are two massless representations, which are distinguished by some other quantum number. Do you see some sign of the fact that there are two rather than one set of massless modes, or not yet?
No, but we haven't looked much in detail at massless modes, so I don't.
Thanks.
I don't have an answer.
Just yeah, one question. Have you or anybody you know actually tried this method on an ADS7? I mean, because you don't seem to. I mean, it doesn't seem to be so important what model it actually is. You can just use this methodology, and that's. I mean, the six. There's also something interesting in duality space, right? Some duality in these mysterious six-dimensional theories.
What would be the super conformal algebra in that?
It's some 1,0 theories, these mysterious things where also nobody really knows how to write them down. But that doesn't seem to be a problem for this approach, right? If you, so, but you have, I mean.
Yeah, no. I don't know if anyone has tried.
I think there were some statements by Linus Wolf that the ADS sigma models don't make, I mean, cannot be integrable or something. But anyway, thanks.
Any other questions? If no, thank the speaker again.
So don't forget, we have the photo session on the north facade of this building in 5 minutes. And then we walk to the restaurant. So please pay attention. If you need a certificate of attendance, then please visit the secretary in the break, okay? Because that's the last chance to get it, and we should print. The other thing, you have this cup. Actually, it's a souvenir you can bring with you, okay? Don't give it back.
Okay, welcome everybody. So it's my pleasure to introduce the first speaker of this afternoon session, which is Lucia Cordova. She will talk about UV behavior of an integrable model. Thank you.
Well, first of all, thanks to the organizers for inviting me to speak here. It's a great pleasure to be in Budapest. So today I will tell you about this work we put out last year with two great collaborators, Stefano Negro and Fidel Shaposnik Masolo. And the long-term goal behind this project is to try to understand what is the space of quantum field theories. And for this talk and this conference, just the integrable quantum field theories. So in practice, what we did in this work is very simple. We studied different integrable models defined by some S-matrix. And then we solved the thermodynamic Bethe-Ansatz equations to understand what are the possible UV behaviors of these theories, in particular looking at the ground state energy of the theory in a cylinder. So this is the outline of the talk. First, I will discuss some motivation. So namely, I will talk about two possible ways in which we can explore the space of QFTs. One is irrelevant deformations, so in particular TT bar and generalized TT bar deformations. And the other one is the S-matrix bootstrap. And then I will review some setup and numerical method. So as I said, we will be using the thermodynamic Bethe-Ansatz. So I will just review some things about it and the numerical method we're using to solve these equations. And then I'll pass to the results. So we started different models. One is called elliptic Sinch-Gordon model, which has infinite resonances. Another one will be theories with one stable particle and an arbitrary number k of resonances. And if I have time, I will also talk about, to our knowledge, a new set of UV complete theories, which are related to the formations of minimal models. So some bosonic analog of those. And I will end with some final remarks. Okay, so let's pass to the motivation. The first thing I want to talk about is TT bar. So the idea is that you can start with some known theory described by some action A0, and then you deform the theory with some irrelevant operator with some parameter alpha. And this operator is constructed out of the stress tensor of the theory. So even though this is an irrelevant deformation and we would expect to lose control over what we're doing, these are actually solvable in the sense that we can compute exactly some observables in the deformed theory in terms of the undeformed one. So for instance, if we're looking at some energy level, we can see we can extract this energy in the deformed theory in terms of the undeformed one in this way. So to give an example, if our original theory here is a CFT, we know that the ground state energy will be something like this, so central charge over R. And if we solve this equation, we will have some quadratic equation. So we get these two different branches and this form with a square root. So since what we are doing is more similar to one specific sign of alpha, I will focus on what happens when alpha is negative. So here I'm plotting this function here, well, a related one, which is the effective central charge, related in this way to the ground state energy. And what you see is that you have some first branch here, which in the IR is related to our undeformed theory, DCFT, so it goes to C. But then as you go towards the UV, something happens at some critical radius, and you have another branch, the second branch here, merging, and below this you have some complex values. So this critical radius here gives us some Hagedorn temperature. Since you can see that computing the entropy, you would get some density of states that grows exponentially with energy. So this signals some Hagedorn transition. However, the physics of the second branch and these complex values is not understood. It's still an upper problem to give a physical interpretation to this second branch of solutions or the complex values here. And finally, something I'd like to remind you of is that you can also define this deformation as with its effect on the S matrix. So if we have some 2 to 2 S matrix S0, the effect of this TT bar deformation is simply dressing it with some phase here. Okay, so this is about TT bar. Now I'd like to go into generalized TT bar deformations. And these are relevant for, okay, I shouldn't use relevant, but these are good for interable theories. So as we know, we have infinite currents in interable theories. So we can construct other operators, irrelevant, out of these higher spin currents in a similar way to TT bar. And the only thing I will use about these deformations is really their S matrix definition. So since we are keeping integrability in the spectrum, we can parameterize this factor phi in terms of CDD factors. So they obey unitarity and crossing. And in general, we can express it in this way. So there is a part which is expressed in terms of rational CDD factors, and another one which gives you an entire function and has this exponential form. So for the TBA, it's easier to understand this exponential form. It was already done in this paper here. It basically changes the driving term. And, but this other product of rational CDD factors is not well understood what happens in the TBA. So we will focus on this part here. And also, since we're keeping the spectrum of the theory, these parameters theta j should be such that they give only zeros in the physical strip of the S matrix, so they are resonances. The effect of this factor here is to introduce resonances to your theory. So yeah, I will focus on these rational CDD factors. And now let me pass into another approach we can take into studying the space of QFTs. And this is the S matrix bootstrap. So the idea is quite different in principle. What we want to do here is explore the space of consistent S matrices, that is, S matrices that are compatible with unitarity, crossing, and analyticity. And what one does is to set up some optimization problem in which you put bounds on the space of couplings. So this allows us to have some nice pictures of theories that are allowed inside some volume, and they are disallowed outside. So this approach is quite general. You can use it for any QFT. But if you do it for 2D theories, then interable theories come up naturally. So they usually saturate bounds, and they live at some special points in this allowed region. So To give an example, there is this monolith here, which is a space of allowed theories with some ON global symmetry and no bound states. And if you just plot a subsection of the allowed space, you see that it has some very interesting geometrical features, and that at cusps of this object, you have some interesting theories. Well, one is just free theory. Then there's another cusp here, which is the ON nonlinear sigma model, another iterable S matrix. And there's also another point here, sitting on a special point, which is also iterable, and it's what we call periodic Yang-Baxter model. So the S matrix was actually written down a long time ago here, but it has some funny properties. So one of them is that it is periodic in the real rapidity. So it tells you that the S matrix looks the same at different energies, which sounds strange. And also, there are infinite resonances in this theory. So there is no known model to it, no Lagrangian. However, you see it popping up at some special point in the monolith. And generically, also for non-iterable theories, you see that S matrices living here at the boundary of the allowed region also have infinite resonances. So it seems to be a generic feature of these optimal solutions. But of course, we would like to understand if these are physical theories, and in particular, what's the UV nature of the models with such S matrices. Okay, so even though these approaches seem quite different, you see that they share various things, in that in the end we're considering some consistent S matrices and trying to figure out what are the features of the models giving these S matrices. So this is the motivation. Now let me go to the setup. So as I said, we will be using the thermodynamic Bethe ansatz, which you'll probably know very well. But let me review some aspects. So the idea is that you put your theory in some finite size cylinder of circumference r, and you want to compute the ground state energy. And this ground state energy, you compute it by solving this equation for the pseudo energies here. And in this case, and most of what I will say, there will only be one stable particle of mass m, so it's a single equation you need to solve. And the input about the theory is inside this kernel here, where the S matrix appears. So here I'm also writing two possible signs, depending on the type of S matrix that we have. So if at theta equals 0, it's -1, it's fermionic, and +1, it's bosonic. And finally, we also have this parameter r, which is some dimensionless parameter given by the radius and the mass of the stable particle. Sorry, I'm still dealing with some post-COVID throat. All right, so once you have these pseudo energies, you can compute the effective central charge with this equation, which is related to the ground state energy in this way. But from now on, I will just plot this function here. So in a typical scenario, what we would find is the following. So since we're dealing with some massive theory, in the IR, we have just a trivial CFT, so it goes to 0. And then in the UV, we should recover the UV CFT. So we would get the UV central charge minus the dimension of the lowest operator. So for unitary theories, it's just the central charge. So it looks like this for the conventional theories. But we will be dealing with something more like TT bar. Okay, so now, before passing through to the numerical method, let me review some analytic aspects of it. So in general, it's very hard to solve these equations analytically. but we can say some things about certain limits. So in this very nice paper, which we're doing some sort of follow-up, really, it was explained what are the possible asymptotics in the IR, so when R goes to infinity. So there are basically two options. One is that the pseudo-energy goes like R cos theta, and this gives you the usual scenario here with C going to 0. And another possibility is that instead it goes like minus R times some other function, and this function changes sign. So it's positive in some region of the real line. And this will give rise to something that instead of going to 0 goes like R squared, which is the same as for TT bar, except that for TT bar you have that the pseudo energy goes like this, but it's only possible for that particular kernel. If not, then the other possibility is just this one. And in order to have this second branch, a necessary condition is that the kernel satisfy this equation, well, inequality. So the L1 norm of the kernel should be bigger than 1. And what this integral does for you is basically it counts the number of resonances minus bound states in the theory. So this is an important condition because it tells you that if you have more resonances than bound states in your theory, then this second branch of solutions is allowed. So this is for the IR, but it doesn't tell us if you could have some bifurcations at some finite R, or in general what happens at finite R, but it's already a good thing that you have this condition explicitly. And the other thing I will use is that in the UV, when R goes to 0, if your solutions tend to some plateau, which is often the case, then one can use the so-called dialog trick to compute the central charge. So you would compute it in terms of this L function, which is the logarithm and logarithm, in terms of the pseudo energy at the constant value of the plateau. So this we will use as well. Okay, so now let's go into the numerical method. I don't want to spend too much time on it because I'd rather talk about the results. But okay, so I said it's really hard to solve in general this equation. It's nonlinear, there's some integration. So what we usually do is to solve this iteratively. So we start with some seed pseudo energy, which is often this R cos theta. Input it here, get the iteration number 1, and do this repeatedly until this equation converges and the difference between iterations is small enough. And you need to do this for each R. So you fix R, you solve it, you change some that R, and you do it again. So this method has many advantages. Mainly, it's very simple to implement, and when it works very well. However, it's difficult to deal with turning points or bifurcations. So basically, this iteration stops converging for some R. And it could even be just some instability, so it doesn't find a solution, but it doesn't really mean that you have necessarily some physical singularity in your equations. So what we can do instead is think about these solutions. So what we want to find is the curve of solutions to the TBA, which for visual purposes, you can think about the C function. And we want to follow this curve by changing R here, but this is not the best parameter for the curve. What you can do instead is parameterize this curve in terms of the arc length, S, so that your variables are now functions of this arc length. And then you move a step delta S away in this curve. So in a cartoon, what you would do is, suppose you have already a solution to the TBA, so some point in the curve, x0. that you could get, for instance, with this iterative method. Then you want to find some other point, x1, delta S away, in this solution curve. So if you compute the tangent vector here to this point, basically you need to solve these two equations. One that tells you that you are delta S away from your original point, so somewhere along here. And another one that tells you that you're actually solving the equations, in this case the TVA equations, so that you're here. And in practice, one does this through some predictor-corrector method. So you have some initial guess for the solution here along the tangent vector, and then you can use some Newton-like method to go into the actual solution. But, okay, it's a bit abstract, but the punchline is that there is a very well-known method in the numerics community. You can see, for instance, this book, to deal with these turning points and bifurcations. So we can implement it in the TVA, and it works very well. All right, so now let me talk about the results. And as a warm-up, let me tell you about the fermionic and bosonic Sinch-Gordon model. So this is really the simplest test matrix. It's just one CDD factor, a single resonance. So in the rapidity plane, you have only 1, 0 here in the physical strip at some theta equals psi pi a. And then you have the crossing symmetric 0 here. So it's a very simple S matrix. And for the fermionic model, really the Sinch-Gordon model, we know the Lagrange and everything, and we have a normal flow. So we have C equals 1 here in the UV, and we flow to 0 in the IR. And if you change A, then it changes a bit how you get from 1 to 0, but you only have, you have the same in the UV and the IR. So this is standard. But what happens if you consider instead a minus sign in front of this CDD? And this was already studied partially in this work by Musard and Simon in 1999. So they saw that the TVA stops converging at some point, and it should have some complex solutions below that. So we just ran the numerics for different A's and got all the solutions to the TVA equations with a minus sign here. So you can see that the critical radius depends on the details of the theory. So here, this coupling A. And, but if you go to the UV, you get the same thing. And this value here, 1/2 plus 0.6i, you can get explicitly from this delogarithm trick with this function here, where the constant solutions to the TVA are basically the solutions to this equation. So you're solving the TVA at r equals 0 with epsilon constant. So I will talk more about this later, but basically one can think of this extra minus sign as adding some other resonance to the fermionic model. So if we go back to the condition on the kernel counting resonances minus bound states, we see that then it makes sense that we have these two branches, because it's really like having two resonances in the fermionic theory. All right, so this is a warm-up. Now, another model we studied is the elliptic Sinch-Gordon. So instead of one resonance, you have infinity. And it's also periodic in the real rapidity plane, so real rapidity direction. And the S matrix is basically the same CDD factor, but now you change the signs to some Jacobi signs. And now, instead of just A, some parameter, you have 2, L here, the modulus, which, if you look into the analytic structure, it's what gives you the period, so the spacing between different zeros, the resonances in the theory. So some limits of this S matrix is that when A goes to 0, you recover free theory. And another limit is when this period goes to infinity, And this is when you recover the Sinch-Gordon model with just one resonance. So we did this for many A's and L's, and this is a representative of what we find. So we see that we have a situation more like TT bar. So there are indeed 2 branches in the IR, but you always have 2 branches. Now it's just complex, and they're complex conjugate to each other. And you see again that this critical radius depends on the parameters of the theory. So here both on A and L. Here I'm plotting varying L and keeping A fixed, but we did it for both, varying both. And another thing to notice is that in the UV, this effective central charge goes to 0. So it's very much like TT bar, and it actually makes sense because you can approximate the TT bar S matrix as some infinite product of CDD factors. So just to show how this radius varies with A and L. So for the bosonic model, we have this orange line, and the fermionic is this blue one. So if you keep L fixed and vary A, you have something like this. So it varies, not so much. And here I'm also plotting for reference the bosonic Sinch-Gordons, or just one resonance. And if you vary L instead, you see that the critical radius changes, and that as L goes to 0, you should recover the Sinch-Gordon model. So indeed, the bosonic one goes to this value, and the fermionic one goes to 0, as it should, because the fermionic Sinch-Gordon model doesn't have this critical radius. Okay, so we did one resonance and infinity. Now let's do everything in between. So before that, let me talk about this map between fermionic and bosonic TBA. So basically, if you have some bosonic TBA equation, you can map it to a fermionic one if you do this identification between the pseudo-energies and the kernels. Note that the kernel has some extra delta function. And this delta function, you can see it as the limit of one CDD factor where the mass of the resonance goes to 0. So this is why the bosonic Sinch-Gordon is like 2 resonances in the fermionic one. So yeah, in general, you have this map between K plus 1 resonances in the fermionic and K in the bosonic. So let's stick to the fermionic ones. And well, we ran numerics for various values of Ks, and then just computed some analytic behavior in the UV. So we indeed saw all these plateau solutions arising in the UV, so we can just use this dialog trick. And basically, the equation you need to solve in the UV is this one here, where y is, well, the y function, which is exponential of pi naught pseudo-energy. So you see that this will give, in general, k different solutions. However, in the TBA, you only have two complex conjugate. And the 2 that are picked by the TBA is actually the 2 that would minimize the absolute value of the central charge in the UV. So we find this very curious. And in pictures, you can see how this happens. So for k equals 2 in the fermionic, which is like the bosonic Sinch-Gordon, you find two solutions here. For k equals 3, you find 3. But the 2 that are picked by the TBA are these 2 ones. And well, you go on, and you see that as you increase k, you're basically populating this unit circle here. And the ones that the TBA chooses are the ones that are closer to y equals 0. So if you instead see what this means for the central charge in the UV, and you plot this in the complex plane, so this is real part and imaginary part, you can see how it changes as you increase the number of resonances. So for k equals 2, you recover this number, 1/2 plus 0.6i. And you increase k, and you go along this curve. And if k is very large, then this number goes to 0, as we saw for the elliptic Singe-Gordon. So I find this quite cute. And the punchline is that we always get just 2 branches and some sort of C-minimization. So yeah. Now, what about theories with more stable particles? What about S matrices with bound states? So this is largely unexplored, but something we did was to study some very simple S matrices that arise with this phi 1,3 deformation of the non-unitary minimal models to 2n plus 3. So now you have n different particles, and their S matrices are given by CDD poles. So we want to see what we would get from theories like this. This one is well known, so you know that in the UV, you would get this effective central charge corresponding to 2n plus 3. And what we did was to deform this theory in the simplest way possible. So we're just multiplying by a minus sign, an overall minus sign everywhere. And what we found is that actually you still have some UV complete theory. So you don't have any turning points or anything. And we computed these numbers for different n's. And here is the label of the minimal model and the number of particles. This is for n equals 3, but we did it for many others. Sorry, I should explain better this plot. So in black, you have the effective central charge, and in blue, the contribution of each type of particle. So it goes for n equals 3 to some number, 0.72 something something. So it would be great if we could construct some physical model for this theory. We don't know, we didn't see anything in the literature. And moreover, except for n equals 1, it seems to be some irrational number. So if these numbers speak to you and you know what they are, please let me know. So yeah, this is just one exploration, but of course we can do more with bound states. Okay, so let me end with some final remarks. So we analyzed the TBA equations for different models, mainly with one stable particle and an arbitrary number of resonances, both in their bosonic and fermionic flavor. And in all cases, except for Singe-Gordon or k equals 1 in the fermionic model, there is a turning point in the TBA with 2 branches. And something that is new to our work is that we were able to follow all the solutions all the way to the UV and find these complex solutions. And yes, I said we always have 2 branches. And there is this curious fact that the UV solutions are such that C is minimized. So regarding more stable particles, I talked about some new to our knowledge family of UV complete theories. But it would be great if we could really classify, if we have n bound states and k resonances, what are the UV complete theories and what are the ones that are not. And here I should point out some recent work which goes in this direction, but for massless flows. So one punchline of the talk is that we find evidence to this conjecture that really the determining factor to get a critical radius or a Hagedorn temperature is the fact that the number of resonances and bound states is less or bigger than 1. And the second punchline I want to make is that most consistent S matrices that we can think of will not be the conventional, will not have the conventional UV fixed point, simply because you can always add some CDD factors with resonances. And since we find this complex solutions and some sort of minimization, it is very tempting to think that in the UV, maybe there are some complex CFTs behind all this. But this is something we need to explore further, so we need to do some excited TBA to learn about excited states, maybe do some conformal perturbation theory. But the message I want to give is that instead of just discarding this series as unphysical right away, perhaps with these universal features, we can try to understand what they can teach us. And with this, I'll end. Thank you very much.
Thank you very much. Thank you very much for the nice seminar, an interesting seminar. Are there any questions? Okay, I may start with a question. So, the fact that you only have square root singularity, can you prove it through TBA? I mean, is it due to the particular specific form of TBA where you have this integral over the real axis?
So I don't know how to do it analytically, but in all numerics we did, it's really happening. So maybe, yeah, there is a way to do it, but we don't know. Yeah, we don't know how to get these critical radius starting from this some S matrix, get some analytic function. We don't know.
So there is no way of forcing the solution in the ultraviolet to be one of the other solution, the other effective central charge you get. So is it, you know, can you think about a way of forcing the system to?
Yeah, I understand what you mean. So one thing, numerically, it's very hard to do R equals 0. But if you do finite R, like close to R equals 0, you can actually be sure that there are only two branches because, yeah, in the numerics, we can do perturbations and just explore this space, and you always land on just two solutions. And moreover, for K large, the solutions, you have many solutions close, so they would also be close in the TBA, well, in effective central charge. And so you should be able to find it with perturbations, and you don't. So yeah, I think, no, you just have these two.
Okay, yes.
So since you did this extensive numerics, I was wondering, have you tried to fit sort of the correction to the central charge? Because from this you can figure out the dimension of the perturbing operator.
Yeah, this is something we want to do, but we haven't done yet. In practice, it would be much easier to do for some small k, because yeah, it's harder to parameterize infinite resonances, and this goes to 0, you see, very abruptly. But yeah, it's something we want to do.
So one slightly tangential question, you mentioned the TT bar deformation in the beginning. So in TT bar, there is always this square root in the result. And in principle, one could choose two different signs of the square root. Well, the second one is non-physical, but I wonder what do people think is the best interpretation for this sign thing? Yeah, I think it was discussed some time ago. I would like to ask what is the present status?
Yeah, I'm probably not the best person to
do
answer
maybe
this
have any
question,
comment
but
on
I
it?
know for this negative sign, you usually think more of an effective theory that is valid up to that scale. This is for the first branch. And for the other branch, it's really an open question, but I think it's nice to see that you can only have two branches, so maybe we should try to answer this question.
So can you show this picture of monolith from the beginning?
Can I show the structure of?
Monolith. First picture on your slides.
No. This?
The very
The
first
stone.
one.
The monolith. Sorry, I didn't hear what.
This one, yes.
Yes.
So you say it's all S matrices with no bound states constrained in this region. So I believe then I could imagine that big part of the boundaries is the places where some poles entering S matrix to become bound states. It's my guess would be. So there are some poles outside of the region when they can form bound states, they enter S matrix, and just reaching the point when it can become bound, and this will be the boundary. This is, I would guess so. Then, is it so? First question, and then if yes, then can you like make some kind of mass gap? So requires that poles quite far away. So maybe you can get isolated point of something.
Yeah. Okay. So yes, in practice, if you have some bound states, then basically you have poles in the S matrix. So this picture can go up because there are poles. So let me explain this better. So here what I'm plotting is the 3 different channels you have for ON at some given point inside the physical strip. So if you can have poles inside the physical strip, then of course this space can be bigger. In practice, for this S matrix bootstrap, since you need to fix some ansatz for the S matrix, you are inputting the analytic structure. So you're really saying, okay, I have poles or no poles. So yeah, the way it's been done so far is that you fix the spectrum and get something, and then, okay, if you have bound states, you get something else. But it should be true something like you say, if you put some bound on the residue of the pole and change this parameter, you should be able to see how this allowed region goes up and down. What is the question?
Roughly. So the question, can you ask that poles do not approach even close to the physical strip? So they on some distance from the physical strip. Can you ask this? And it would be smaller thing.
The poles, you mean the bound states or the ones coming from the resonance on the second sheet?
Those who are not bound states. Some poles that are not bound states, they can be very close to the physical strip, and they should be on the boundary of the monolith, such
but
series.
Outside the physical strip?
Yes, but very close. Can you increase the gap?
Yes, so this is definitely inside this region here. And yes, so another way to phrase what you're saying is, can you fix the mass of the resonances in the theory? And yes, you can do that and play this game. So for instance, if you want to find a particular model like the nonlinear sigma model, this is one way to do it. You fix the mass of the resonance and you do get this point.
So what if the parameter of the resonance is complex, like in the staircase model, or you have many staircase factors?
Yes, I should have said something about this, so thanks for the question. So in this paper by Samologicos, well, all these authors, they explored precisely this question. So they considered 2 CD factors and all the ways in which you can move the zeros in the S matrix. And so they also saw that you always have 2 branches, and the critical radius would depend on these parameters. But as I was showing, really what matters is just the norm of the kernel. So if you have 2 resonances, you will end up in the same UV point.
Okay.
Yeah, but maybe it's also interesting how you approach, no? Because in the staircase model, not the very end is important, but all the way along you go and visit other minimal models.
Right, but yeah, if you have another CDD factor, then you won't have this, well, maybe you have some other, I don't remember exactly what happens there in this other paper, but you have this other different behavior. So it's not like you're approaching some minimal models in the IR.
Okay. So I have a final comment. I mean, this arch continuation might be a very powerful method to study also excited state, because
yes,
also in that case, have you tried that for some simple model?
Not yet, but it's in my to-do list.
Yeah, because it might be also useful for
DSCFT. And we would need to do this because most likely if you do the excited TVA, you will also get the singularities, etc. So you need to deal with this method, yes.
Okay, thank you very much.
Thanks.
Very nice. We have to wait the speaker. Okay. You ready? Okay, next speaker is Ilya Buric. He will talk about Godin integrability and then harmonic analysis of conformal partial waves.
Okay, do you hear me? Yes. Okay. First of all, thanks for having me. I wish to thank the organizers and for putting the conference together, which has been most inspiring. I will talk about some work with various subsets of these collaborators, which are Misha Isachenkov, Sylvain Lacroix, Jeremy Mann, Lorenzo Quintavalle, Volker Schomerus, and Zhenya Sobko over the last few years. The general topic is conformal partial waves in higher dimensional CFTs and their relation to integrable Schrödinger problems. Just to say a few words, partial wave decompositions in general in quantum field theory are one of principal analytic are one of principal analytic tools when you want to isolate now? Is it better? Okay. When you want to isolate kinematically fixed part of some amplitude from the dynamics. And for example, in 2x2 scattering, you will have decomposition where all states of spin J will give you a Gegenbauer polynomial of the scattering angle, and then you will have a dynamical function of the energy. In conformal field theory, this idea is completely analogous. So we will have a 4-point function, which is decomposed in kinematically fixed partial waves, which are multiplied by dynamical OP coefficients. And the difference is that now partial wave sums over states that transform in a single representation of the conformal group that propagate. And why we are doing is the conformal bootstrap. So we should have this in back of our mind. And this is a set of methods for extracting OP data from the crossing equation. So this is the crossing equation, and if you know the partial waves on both sides, in the S channel and in the T channel, then you can cook up some smart functionals and act on this equation. And these people have done this with impressive results. So for example, this is this famous picture for the scaling dimensions of the Ising model, where from a single correlator, you get this bound on the allowed region in the scaling dimension space. And if you consider mixed correlators, then you get a very small island, so which essentially pinpoints down this theory. So in order to study crossing equations, we need these partial waves, and it's very easy to define conformal partial waves as to give an integral representation for them, which is, however, not very useful, and it's difficult to evaluate. And big step in understanding of these functions was made by Dolan and Osborne, who understood that one can write a second-order differential equation called the Casimir equation, they also solved this equation in terms of hypergeometric functions for in even dimensions. But even having the equation is pretty good from the bootstrap perspective, because you can develop fast methods for example, series expansions in, for example, these radial coordinates. And since the work of Dolan and Osborne, indeed many efficient methods have been developed for computation of partial waves with external scalar or spinning fields. And these include these methods here that I wrote. So differential shifting operators which shift external dimensions, then these expansions in radial coordinates, recursion relations, and then also the weight shifting operators which allow you to construct all partial waves just from scalar ones. And okay, there is also this method which I singled out because it will be important for the talk, by Volker, Misha, and Zhenya, who realized that the Dolan-Osborne equations are equivalent to the two-particle integrable Schrödinger problem, which is this BC2 Calogero-Sutherland Hamiltonian. So one of the problems that I will talk about is how about higher point partial waves. Much less is known about them, except in low dimensions. In 1 and 2 dimensions, they're known. And if you have only scalar exchanged fields, they are also known. And there is also some work on constructing partial waves for spinning fields, but much less than for 4 points, for sure. And you may ask, why do we want these? And let's say there are two maybe principal reasons to study higher point partial waves. One is, ideally would be to have abstract bootstrap for higher point functions, which we don't at the moment. Although when the points are in light cone configurations, so if you have, for example, 5 or 6 points, so that each two consequent distances are null, then people have already done the Porto group bootstrap, analytic bootstrap in these configurations. But you can also be less ambitious and just compute some higher point correlator in some theory to, for example, to first order in epsilon in the Wilson-Fisher fixed point, and then if you know how to spectrally decompose, then this contains infinite amount of OP data. So this would be another useful application if you had higher point partial waves. Okay, so the Sorry? It's independent of the theory. I will come to that in the talk. So yes, the questions that I want to answer or partially answer in the talk are, in what sense are these partial waves integrable, and also to ask, are there elements that you may reasonably call universality in kinds of equations that partial waves satisfy. Some of our results are the following, that in general, for an n-point correlation function, the partial waves can be constructed as eigenfunctions of a particular Godin model, which is adopted to this correlation function in the OP channel. And then there are two other results. One is about 4-point functions, and they're related to Calogero-Sutherland models, which is an older story, but maybe the word spinning here is relatively new. And then the 3-point functions of spinning operators turn out to be related to a certain elliptic Calogero-Moser model, which was defined by Tingoff and collaborators. And as a byproduct of this analysis, we will get some relations between these integrable models involved, because on the left, we know that in the conformal field theory, there is a operator product expansion, which allows you to reduce an n-point function to an n-1 point function. And this process produces some relations between these models on the right-hand side. Okay, so this will be the results. The set of differential equations that completely characterize these higher point waves. And okay, these equations will be hard, but as a first step, we can already see some structural properties of solutions, like factorizations in certain limits. Yes, and okay, this relation between models that I mentioned. Okay, so I will start with the 4-point functions, which is the best studied case, and we know most about it. But I will try to explain how does a relation to these Calogero-Sutherland models come about. So the starting point of this analysis is the two-particle little group, which you can easily see the stabilizer of 2 points inside conformal group, which you can see is isomorphic to this group K. And you can see this if you put 1 point at 0 and 1 at infinity, then you have dilations and rotations which fix this configuration. And then if I look at a 4-point function and view it as a 2-point function of 2 particle states, the space of solutions to word identities is something like this. So I have twice G over K, and then word identities tell me that I need to space at the that I need to look at the space of G invariants inside here. And then you can sort of cancel, this is very schematic, one of the G's inside with the G outside, and you get this double quotient by K of G. But notice that K is not any old subgroup, it's what is called a spherical subgroup. So it's fixed by a second order automorphism, and the quotient G by K is a symmetric space. And these types of double quotients were studied since the early days of representation theory by Harish Chandra, Gelfand, Godamon, and other people. And the main player here is this space of KK covariant functions. So you can consider invariant functions, which are invariant under left and right rotation, multiplications by elements of K. But slightly more generally, you can take 2 finite dimensional representations, rho and sigma, and consider vector valued functions valued in this space Hom W right, W left. So W right and left are carrier spaces of rho and sigma. And then this spherical condition is the condition that this space, when you put representations to be trivial, is in a billion algebra under convolutions. So when you have such a pair of G and the spherical subgroup K, then you have a so-called restricted root space decomposition, which is similar to the ordinary root space decomposition with some slight differences. So we start from the maximal abelian subspace of P, which sort of plays the role of the Cartan, and then we have the centralizer of A in K, which is M, and then some root spaces. And these root spaces are called restricted root spaces. They are with respect to A rather than the Cartan. And then some standard theory shows that we have a spherical decomposition in the universal enveloping algebra, where I can separate, write this as a product as elements in P, in A. A is here, is a billion, and then 2 copies of K. And on the level of the group, this is known as the Cartan decomposition, KAK, which for SU2 is the decomposition into Euler angles. So the idea, because now we have these spherical functions, if I have a spherical function, if I define it on A, I can uniquely extend it by covariance to the whole of G, so they are effectively functions of only on A. So they depend on dimension A variables. And this dimension is called the real rank of the pair. But really the main property of these pairs is that you can reduce any differential operator on G, any element of the universal enveloping algebra regarded as a differential operator. If you just decompose this in the universal enveloping algebra, you can reduce this operator to an operator in just the number of variables on AP. So this is the content of Harish-Chandra's theorem, that this decomposition in the universal enveloping algebra allows you to compute the reduction of differential operators in general. And let me give an example. So if you start from this pair, which is of rank 2, that is relevant for me, the conformal group and this group K, when we reduce the Laplacian and then conjugate some first order terms out, which is sort of a trivial step, you get the so-called Calogero-Sutherland Hamiltonian. And this Hamiltonian is related to the root system, and this is precisely this reduced root system of the pair GK. And yeah, so it's exactly. You conjugate out this cot alpha times t, so this will be some first order term. You conjugate it out, and then you will get precisely this Hamiltonian. Yeah, they are very closely related. And then this spin part are these terms. Yeah, so this Hij, Hi, Aj, so these guys are generators of this abelian group A, and they're replaced by partial derivatives, so they become this dt1 squared, dt2 squared. Then you have a term here which also has some elements in H, which become d by dti, and you conjugate those out. And then you have something which is a spin part, which I didn't. When you conjugate this, you will get this one. So when you conjugate out this term, you will get some potential term, and you will get this one, and these constant terms, this one and this one. And then the spin part is this. And I will now say what these terms are. These M1A, M1A, D squared, and so on. So these guys are generators of K. And the point about this formula is that I don't have to tell you what the representations are. So I can tell you only at the end, rho and sigma were particular representations, and replace now in this. Okay, so here I have written the formula when one of the representations is trivial. So I have put rho to be trivial and sigma will be non-trivial. When both representations are non-trivial, the formula is a little bit longer, and this is why I didn't write it. But if I now want to compute the Hamiltonian with some representation sigma, I will take this formula and replace these generators, which are generators of K, by sigma of them. So this will be a matrix valued, if you will, Hamiltonian. Okay? Does this answer your question? Okay. I will have some more formulas later, so maybe it's... yes, so, and you can reduce any Casimir element, and this is how, one way to see the integrability of the Calogero-Sutherland model is that higher Casimirs give you first integrals. Exactly, so this shows you integrability of the scalar model. So for the scalar model, you will put all these guys to 0, these m's and these, and then you will have the fourth order Casimir, which commutes with this one. And you can check that this eigenvalue problem for this operator is equivalent to these Dolan-Osborne equations that I was mentioning before. Okay, just to say this is not only abstract nonsense. We used sort of this technology, extended it to supergroups in some earlier work, and the extension to supergroups works like you need to put some nilpotent potential perturbation to this Hamiltonian, and then you can systematically, if you know the eigenfunctions of this guy, you can systematically solve for the eigenfunctions of the supergroup guy. And with this technology, we computed some superconformal blocks in 4 dimensions with Forker and Zhenya. And another interesting class of systems that fall under this category is defect conformal field theories. And whenever you have a defect, it is also fixed by a automorphism of degree 2. So it's also of this type. And you can see, for example, then that a 2-point function in the presence of a defect, if the defect has codimension 2, for example, this will be exactly the same Hamiltonian up to analytic continuation. So, of course, this is important when you solve for eigenfunctions, the analytic continuation, but at least, yeah. And one more comment, maybe, that these partial waves in ordinary QFT are eigenfunctions of a similar Hamiltonian, just for rank 1 instead of 2. And the solution theory in general for scalar Hamiltonians of this type was developed by Heckman and Opdam, and the eigenfunctions for any root system are these Heckman-Opdam hypergeometric functions. Okay, so now I would like to go to higher points. I think this sort of explains where this solvability comes from for 4 points. But for higher points, the story is very different somehow. So now I come to this point, defining the conformal blocks. So you can see that Casimir operators, so in the 4-point case, Casimir operators measure quantum numbers of the field that propagates. And when you have a higher point function, these kind of quantum numbers are not, there are fewer quantum numbers of this type than cross ratios. And you can easily understand this because if you have a 3-point function, for example, of 2 symmetric traceless tensors and the scalar, this has a well, the number of tensor structures is greater than 1. So you need some further quantum numbers to specify which tensor structure. If I say, for example, that here is a particular field of spin L1 and here of spin L2, I still need to say what tensor structure at this 3-point function I'm picking. And when you specify all the quantum numbers of the fields and all of these tensor structures at the vertices, then the partial wave is uniquely fixed. You can write this integral representation as a product of, over the product of 3-point functions. What we did in these works was to characterize also the same partial wave as a solution of certain differential equations which come from the Godin model. And in this case, we would have 5 cross ratios and 4 quantum numbers, and the 5th quantum number related to the vertex is measured by this operator, which is a 4th order operator, and the notation here is X is one of the generators of the conformal Lie algebra. So alpha are the indices. So here I am taking the 4th order invariant tensor, and I'm taking the generators at points 1, plus 2, minus 3. So to each point, at each point I have this field representation by differential operators in coordinates of this point. So this is how I construct this operator, and you can easily check that this operator commutes with the Casimir operators. And okay, so how does this generalize to higher points? Okay, so first of all, the space where correlation functions live is the following. So for every point, I have a field representation or non-unitary principal series representation of the conformal group. I take the tensor product of them, and then I need to impose word identities, which means taking G invariants in this space. So this is the space of tensor product of correlation functions. And this is what inspired this, why the Godin model is the appropriate one for the following reason. So the Godin model is defined when you have n commuting copies of a Lie algebra. You attach them to points z1 up to zn in the complex plane. So these are just parameters of the model. And there is the Lux matrix, which depends on the spectral parameter z, which is constructed as this, sum of generators over z minus zi. And from this Lux matrix, you construct the Hamiltonians by contracting the Lux matrix with invariant tensors, and then adding some correction terms, which are of lower order. So for second order, there are no corrections, but for higher order Hamiltonians, there are these correction terms. And then, okay, these Hamiltonians, of course, commute, but they also commute with the so-called diagonal generator. So if I take the sum over all sides from 1 to n, each of these Hamiltonians commutes with this diagonal action. So this means if I attach to these points not the abstract universal enveloping algebra, but the representation, and I will attach these principal series representations, then these operators become differential operators in all space-time coordinates. But the fact that they commute with this diagonal action means that they reduce to this space of invariance. And this means that I can reduce these differential operators to differential operators that act only in cross ratios. Okay. Right, so what about the parameters? In CFT, actually, we don't have any of these parameters. So we do have parameters, for example, characterizing spins and weights of the fields, but those are of different type, because I already put those parameters in definition of this representation. So I don't have any meaning for these extra n parameters. And in fact, the Godin model that will produce these operators relevant for CFT sends all of these parameters either to infinity, one of them is sent to infinity, and then the others are sent either to 0 or to 1 in some particular, at different speeds, depending on the OP channel, so the topology of the OP. Yes, so in little more detail, if I take an edge, so maybe just to have in mind, an OP diagram looks maybe something like this or something like this. So if I take any edge, it breaks the set of external points into two disjoint subsets, and I can take the sum over generators of one of these subsets and form this kind of operator, so contract it with an invariant tensor, and these are precisely the Casimir type operators of Dolan and Osborne. And then I can supplement these operators with these vertex operators where I pick a vertex, and then this breaks the set of external points into three disjoint subsets. And then I again contract, but I have one more parameter in the game, so I can pick, let's say, P, or no, here I called it new. So, okay, I pick new generators from one branch and pick P minus new generators from a second branch. And you never need to use all three branches, because word identities tell me that if I take generators, or if I sum over all generators and hit the correlation function, I get 0. So the third branch is the linear combination minus the sum of first two branches. Also here in the first definition, I need only to take generators from one of the branches. And okay, yeah, in any case, when you do this, you can show, and I have some slides in the back if someone wants to see more formulas, that the Godin Hamiltonians in this limit, when you collide punctures at 0, 1, and at infinity, give you precisely these kinds of operators, so these blue and light blue operators. We didn't prove, but we checked up to 10 points that always the number of independent operators that you are left with equals the number of cross ratios. So, yes. And okay, just to show an example how this works. So, for example, if you have a diagram like this, this is a CFT correlation function, and I am fusing here two external operators, performing the OP, and then with the result, I fuse it with the third one, and so on. And in the Godin model, I will take the sites to be x to some power. So this I is one of these. So depending on the number, I will have a different power, and then I will take x to 0. So this will be the limit. And I will rescale the Lux matrix so that I get a finite quantity. And when you do this, then for every vertex, for example, you get an operator like this. And from these guys, you precisely construct these blue and light blue Casimir operators and vertex operators that I wrote. And if you have a more complicated topology, then if I pick a point, it depends, the way it scales to 0 or 1 depends on a way I go to this point if I start from the top. So every time you go to the right, you need to add a power of x. And in the last step, you need to add a certain power of x as well. It's not very illuminating how it works, but in this picture, for example, there is only one point which is to the right of the top, so only one point will go to 1. All these points will go to 0 at different rates, and the top point always goes to infinity. And okay, so the picture that one gets is something like this. We have some, so how does the counting work? Because the most non-trivial part here then is to really see whether the number of independent operators that you have is the same as the number of operators that you need. Because, for example, if I construct a Casimir from a single site, because I attached an irreducible representation to this site, this is just a number, so this is not an operator. But you can see that the deeper you go in the diagram, these Casimir operators constructed as I said, they will have dependencies, but the deeper you go, you will have fewer dependencies. So at each step, you get one more independent operator. It's like when you have a 4-point function, you have a second-order Casimir and a fourth-order Casimir, and you don't have anything else. But this is true in any dimension. So the, I don't know, 10-dimensional conformal group certainly has more than 2 Casimirs, but they become dependent. And sorry? Oh, okay, I thought I did, but here is the formula. So I take, so this R is some edge in the diagram. Oh, yeah, first you pick an OP channel, for example, this one, I don't know, but any OP channel. You pick an internal edge, you call it R. Then I have two sets of external points, so the ones that are left of the edge and the ones that are right of the edge. So these are called IR1 and IR2. Then this X, so it's some generator of the conformal group. This index means that I take the sum of generators at all points in this branch. So I take the sum of external generators left of the edge. These are these IR1s. So I use them, okay? So for example, if I pick here, if I pick this edge here, and I look left of this edge, I will be summing over generators of 1 and 2 at points 1 and 2. So by this notation, I put an index is a set. An index is a set, and that means that the object is a sum of generators over all elements in this set. So in this case, IR1 would be the set 1, 2, and the generator would be X at point 1 plus X at point 2. And with the vertex, it's similar, just I have a partition into 3 disjoint sets. So if I pick this vertex, I will have 1, 2, 3, 4, and 5, 6. Okay. Yes, so, and indeed, so here, for example, you have 2 external scalars, and in the tensor product of these field representations, only symmetric traceless tensors can appear. So you need 2 quantum numbers to measure the field that propagates here. And then if you have a symmetric traceless tensor and the scalar, you can have representations with two rows in the Young tableau. So you have 3 quantum numbers, two spins and 1 scaling dimension. And you increase always the number by 1 until you reach the rank of the group, and then you cannot increase anymore. So here I wrote it, I guess, in 4 dimensions, where the rank is 3. And then you can also count the number of vertex operators, and the easiest way to count is I mean, okay, this is cheating, but we checked, okay. So you can count it by counting the number of cross ratios and then subtracting this number of edge operators. And this will tell you, for example, that this vertex comes associated with a single vertex operator as well as this one. Whereas in this picture, you have this middle vertex comes associated with 3 vertex operators. But you can also see this in an independent way, like if you consider a 3-point function with a symmetric traceless tensor at one length, a scalar here, and then a mixed symmetry tensor with 2 rows in the Young tableau. And the most general 3-point function, when you write its functional form, it will. Okay, so let me write the functional form. So for example, if you have a, okay, so this is for 2 STTs and a scalar. 3-point function takes the following form. So you have some prefactor times a polynomial of x. So x you construct out of external points in some way, and this polynomial is of finite degree. But morally speaking, you have a single variable, this x, associated to this vertex. And if you do the counting in the same way for a mixed symmetry tensor and a symmetric traceless tensor and the scalar, you will again have a single variable associated to a vertex of this type. Okay, so the system that we studied, how much time do I have? Okay. So the system that we studied with this technology was a 6-point function in this so-called COMP topology of the OP channel. So here I will have 6 scalars, and I will consider, so I have a conformal block. So there is a symmetric traceless tensor propagating here, a symmetric traceless tensor propagating here, and then a mixed symmetry tensor propagating here. I pick basis for the space of tensor structures at my 2 vertices. And I want to say something about conformal blocks defined in this way. So in order, well, okay, so we use the following set of coordinates, which is important. Somehow the coordinates are also adopted to the choice of the OP channel. So for out of the first 4 points, we constructed we use these Dolan-Osborne coordinates Z and Z bar. So these Z1 and Z1 bar are the Dolan-Osborne cross ratios built out of first 4 points, and Z3 and Z3 bar from the last 4 points, and okay, obviously Z2 and Z2 bar from these middle 4 points. And then to define these, so this has 9 cross ratios in total, so the correlation function. Then we have two cross ratios defined in the following way in conformal frame. It's not very important, but yeah, so if you fix the points 3 on a line, and then 2 points will be in some 2 planes, and if you fix this conformal frame, the cross ratio W for these 5 points is defined as the sine squared of half of the angle between these 2 planes. So we have 2 such cross ratios defined in terms of first 5 points and the last 5 points, and then in a similar way we define this upsilon variable defined in some conformal frame for all 6 points. And then the limit that we'll consider is that all these 3 middle variables go to 0. And physically, this means that points 4, 5, and 6 become close to each other. So the distances between these points become 0. And then writing this, there are 9 differential operators coming from the Godin model, and in this limit, 3 cross ratios disappear, they're sent to 0, So there are 6 remaining operators in the limit, but what happens is they all they factorize in 3 left variables and 3 right variables. And then the conformal blocks in this limit factorizes products of these left variables and right variables. And moreover, you can check that the quadratic Hamiltonian, so the quadratic Hamiltonian of the Godin model, it's a 3-variable operator. When you compute it, is the same as this spinning Calogero-Sutherland model. And the spinning model for such a 4-point function, where you have 3 scalar fields and then a field which is a mixed symmetry tensor with 2 Young tableaus. And just to show a formula, so this is this operator. So it's a special case of the operator that I showed in one of the first slides, but now I put, for these abstract generators, I put their representatives in this mixed symmetry tensor representation, and they come with this variable x. So this is this spinning Calogero-Sutherland model, and it depends on quantum numbers of this field. Okay, just to say similarly, we looked at the reduction of a similar type on a vertex, where the model that you get in the limit is this elliptic Calogero-Moser system that was found by Tingo, Felderma, and Veselov. And again, the parameters of this elliptic system, they are related to quantum numbers of this field. Okay, so let me conclude. Okay, so for any correlation function and the choice of an OP channel, we have this limit of the Godin model such that Hamiltonians compute, well, the eigenfunctions coincide with partial waves. We introduce these coordinates which are compatible with taking OP limits and observe this factorization in this particular limit. In particular, this does show that, for example, you get this spinning Calogero-Sutherland model or this elliptic Calogero-Moser model as reductions of Godin in this limit. Some directions for the future. Well, one thing interesting for conformal bootstrap applications would be to look at the light cone limit in a 6-point function, and this is being done at the moment. Yes, so similar to what people have done for the 5 points, where you can get some bounds on OP data by analyzing this limit. Well, conceptually more difficult would be to formulate also the numerical bootstrap for higher points, and this is something we are thinking about, but it's complicated. Then, okay, what about solution theory? This is not really a usual type of Godin model because we have these infinite dimensional principal series representations attached to sites. So some of the techniques do work, like if you are in 1 dimension, then it's possible to go to momentum space. Well, okay, it's possible to do separation of variables, and these separated variables turn out to coincide with momenta, and to construct eigenfunctions in this case. But yeah, it's not easy to do bootstrap, for example, in momentum space. So there's some caveats there. But I think a very promising way to construct eigenfunctions would be to use these weight shifting operators similarly to what people have done for 4-point functions. Our sort of initial idea was to analyze this whole system by reducing it to different vertices and different 4-point diagrams inside, for both of which we sort of know solutions, and build conformal partial waves by somehow combining these vertex eigenfunctions and 4-point eigenfunctions. But it's in the future, it's not so clear how to do it. Among other directions is this universality. You can actually apply this spinning Calogero-Sutherland models appear also for some higher point functions involving defects, where you can somehow transfer some of the spinning. Well, if you have a higher point function, you can treat some of the space-time degrees of freedom as spinning degrees of freedom and map it to a spinning Calogero-Sutherland model with an infinite dimensional representation. And so this is something we've been looking at with Volker. And also the extension of this Godin, with this correspondence to Godin models to systems with defects include these cyclotomic Godin models. And finally, one can also look at ordinary quantum field theory, and spherical functions are also relevant there for computation of ordinary partial waves, which is, I don't know, I mean, it's an important problem. Then you can start looking at scattering of gravitons and photons, for which these partial waves are important. So it's also something that will be interesting to look at. That's it.
Thank you, Ilya. Thank you for the very interesting seminar. So, are there any questions?
So when you do this conformal cross ratio, Z1, Z2 up to many, and W's.
Sorry, can you?
So when you did decomposition of 6-point function into 2, like in the middle, that's that's exactly what you declare you want here. Yeah. So now you kind of have this new partial wave with many points. That's okay. But it feels like you choose conformal cross ratio like very manually, like you design conformal cross ratios Z1, Z1 bar, W1 very manually. Like there are many other choices presumably you can make.
Yes, yes.
And then you say this choice gives me spinning Calogero-Sutherland.
Yeah.
It's good representation because we can see something, but the further you go, the more cross ratios it will be. There are systematics that you can do.
Yeah, well, already, like, for 4 points we have Calogero-Sutherland. If I go to generic configuration in 6 points, I don't have something like this. And indeed, like Godin and the Calogero-Sutherland, I would say, are completely different. So the Godin is super general integrable model. So I can adopt it for any for any endpoint function with anything. I mean, I can also put spinning external fields and so on. The Calogero-Sutherland story is very special, and it applies to this 4-point case and to some cases with defects, and it's not going to appear in general cases for sure. But yeah, one of the things that we are exploring is what is the space of cases where you can reduce the problem to a spinning Calogero-Sutherland, and yeah, for sure not all higher point functions.
Okay, and you mentioned duality between integrable models. I think it's in your plan of the talk at the very beginning. You mentioned new relations between integrable models.
Yes.
Which ones? Where it was?
So, for example, yeah, this. Okay, for this system, we have a Godin model associated with this system with 9 independent Hamiltonians. And then the statement is that if you take this Godin model with this principal series representations and look in the limit where these 3 variables are sent to 0, then the Godin Hamiltonian, the quadratic Godin Hamiltonian, becomes the spinning Calogero-Sutherland Hamiltonian. and also in this case similar.
So it's something completely new, right? People did not know these things before.
No,
okay.
no, they didn't. Yeah.
Okay. Further question?
I have a conceptual question. So does this correspondence to this Calogero model helps in calculating 3-point functions or 4-point functions analytically?
Well, this is purely kinematics, what we are looking at. So, no.
More questions?
I mean, if you do bootstrap, then yes, but like, the way bootstrap functions, you put this into the crossing equation, and then from the crossing equation, you get bounds, either numerical or analytical, on the OP coefficients. But you need to go through this analysis, which is the more difficult part of the analysis.
Yeah, so how does your construction depend on the details of the conformal field theory you're considering?
It doesn't, so it's just kinematics. It works for any conformal field theory.
And let's suppose that we want to look at our favorite conformal field theory, let's say n equals 4 super Young mills. In the planar limit, there is some integrable structure. Does this integrable structure knows anything about the other?
I would say no. I mean, I don't think so. Well, also, like I don't think this has been too much explored. So we looked at super conformal theories computing the blocks actually from our side, supersymmetry adds quite a lot of complications. So to compute super conformal blocks when you have long operators is much more difficult than to compute them in a bosonic theory. And for n equals to 4, no one really, for n equals to 4 supersymmetry, no one really computed these blocks except for all half BPS operators. So I think this what we looked at was n equals to 1 with 2 long and 2 short operators. And I think this is the only crossing equation with all conformal blocks put in 4-dimensional superconformal theories which is not only for short operators. So maybe if one computed these superconformal blocks for n equals to 4 theories, maybe something would be seen, but in general I don't expect. They just get more complicated when you increase supersymmetry.
Okay, thanks. And I have another conceptual question. Does this help for bootstrap? For example, can one use this kind of information for if you want to do bootstrap?
You mean of higher point functions or?
Yeah, let's say.
Yeah, so it helps. So, for example, sorry, which slide? Yeah, so what Vaško, Raul, and Shinan did in this paper was they computed in n equals to 4 a 5-point function of this O2 operator, and well, in super-great limit in expansion, and they spectrally decomposed it. And when you have a 5-point function of this operator, there are many non-protected operators that appear in the OP that propagate there. And by spectrally decomposing a single correlation function, they got a wealth of OP data to this order. So if one, but this is a very hard computation. So it's not just you can sit down and do it, but if people could, then this would give an enormous amount of OP data. So this is the goal or one of the directions.
So further questions? So if there are no further questions, we can thank again Ilya. We have now a half an hour break. Start.
So it seems you experienced some problem with the Wi-Fi. So the suggestion was that maybe you should try to change the last digit from 7 to 6 or 8. It might work. Okay, thank you.
Okay, the last speaker of today is Setwan Seng. He will talk about bootstrap, the lattice Young-Mills theory.
Okay, shall I start?
Yeah, I think you can start, I think.
Okay, good afternoon. It is my great honor to present our work, Bootstrap the Lattice Young-Mills theory, collaborated with my PhD supervisor, Volodya Kazakov, who is a real expert on matrix model and integrability and who teach me a lot during our collaboration. Okay, what is Bootstrap? This is one of the mostly abused terminology in every aspect of science. For example, in the computer science, it sometimes refers to a framework in the web development. But literally, it actually means these parts of the shoes. It is not shoelace, actually. And in today's talk here, we mean that basically it is solving the theoretical physics problem by optimization theory. We will start with a toy model, or if I rather prefer to call it a prototype, because although it will be very simple, we will say that it captures the most important construction of our bootstrap method to lattice Young-Mills theory. Okay, let's talk about the motivation. The motivation is first, it is a fully non-perturbative formulation. And we will see that the bootstrap method gives us the rigorous upper bound and lower bound on the dynamical quantities of the system. And also, it is not only theoretically interesting, but numerically competitive. We will see that in some area, it can already beat the standard numerical method in most of the physics area, that is the Monte Carlo method. Okay, let's begin with some very brief introduction to the optimization theory. Actually, maybe some of you don't know the name, but you must know this kind of problem. For example, the quadratic programming. That is minimizing a quadratic polynomial. Just minimize a quadratic polynomial. And also the linear programming. That is minimize a linear combination of some variables under some linear inequalities or inequalities. This seems very simple and naive, but imagine that you have 10,000 of variables and 10,000 number of equations or inequalities. Then finding an efficient algorithm to solve this problem is not an easy task, actually. And the most important kind of optimization problem we will be talking about is actually semi-definite programming. That is, we minimize some linear combination of the variables under a semi-definite condition of a linear matrix. We notice that the previous two kind of programming, that is quadratic programming and linear programming, they are actually special case of this semi-definite programming. For example, linear programming, you can think of it as under a semi-definite condition of a diagonal matrix. And all these kind of programming, they fall into the class of convex optimization. That means we are minimizing a convex function subject to a convex set. Let me remind you briefly what a convex set means. That is, there is a set in the Euclidean space that you have 2 points in the set. Then the middle point of any such two point must be also in this set. Then this is convex. For example, a linear line, it must be convex. But such nonlinear line or nonlinear equation, it must be not convex. Why? Because think of a parabola. That is, if you take any different 2 points, the middle point of a parabola is not also on the parabola. But I simply notice that nonlinear equation cannot be convex, but nonlinear inequality can be convex. How to say that? Well, the region inside a parabola, it is convex. This is very important. This will be very important in our following this construction. And generally, if the problem, optimization problem, it is not convex, then generally we cannot solve it. This means that when the scale of the problem goes large, the level of difficulty will grow exponentially, that it will be hopeless to solve it. And in the computational complexity theory, this kind of non-convex problem, this is NP-hard actually. Okay, so let's begin our toy model that I would like to call it zero-dimensional phi-4 theory. Actually, it is as simple as it could be. It is a single variable integral. Here we take it as a partition function. So we want to use bootstrap to solve its moments, actually. All the moments under this partition function, that is the expectation value of x to the k. Let's see how the bootstrap works here. Of course, we have a lot of methods to deal with this problem. The bootstrap problem method first begins with actually the Schwinger-Dyson equation. We do a minimal shift x to the x plus minus to get some linear equations constraining different moments. Actually, this is equivalent to that you continuous to the integration by parts, then you get this kind of equations. And then we have the global symmetry. That means from the symmetry of this model, we can see that it has a x to the minus x symmetry, so that the odd moments must be vanishing. So we have the global symmetry. Although this condition looks naive, actually this is independent from this kind of Schwinger-Dyson equation. So we must take it, for efficiency, we must take it into account. But through these two equations, actually we can solve all the higher moments. Higher moments means k larger than 2 by add some linear combinations of W2. But for the W2, we cannot solve it. We can check it actually here. The k goes from 0 to infinity. So we cannot solve W2. How to solve W2? As long as we can have a very precise estimate of W2, then this problem is solved. Well, we have this simple observation that any square of polynomial integrated over the quartic measure is positive. This is as naive as it could be. But we notice that this must be true for any alpha, that is any vector alpha. So this equation, actually it is a quadratic form of the vector alpha. So this always true means that if the matrix correspond to this quadratic form must be positive semi-definite. This is just a definition. What's the matrix? Well, this is the matrix. We can check it. The WK, I remind you that this is just a case moment. So we can extract this matrix. And this matrix is actually equivalent to a series of algebraic inequalities of W2. I remind you that we already solved all the higher moments by add some linear combinations of W2. Okay, so we formulate this problem as a semi-definite programming actually. We can, under these conditions, we can minimize or maximize W2 such that this matrix, we will call it later correlation matrix because it's a matrix of correlation functions. This is positive semi-definite. For the numerical reason, of course, we will put some truncations on this matrix. Let's see, W lambda is the top lambda plus 1 times lambda plus 1 of the matrix. Okay, so how does it work? Of course, our conditions, our constraint, we just wrote, it must be correct. But the result could be totally trivial, but it seems not. Here, this is the analytical result. You can always get it from Mathematica. This I and k, they are some modified Bessel functions. And this is the numerical result at g equals 1, lambda equals 10. This is what you get from minimizing W2. And this number is what you get from maximizing W2. In the middle, this is the analytical result. So we can see that this is already a 5-digit result. So this is highly non-trivial. This is the plot. As we increase lambda, we see that the allowed region of W2 shrinking very fast. Actually, for lambda equals 12, the upper bound and lower bound is already indistinguishable. Okay, this finishes our bootstrap of this toy model. Here is several remarks. First remark is that in some aspect, we are already much better than the weak coupling expansion. Why? If you do the weak coupling expansion at g equals 1, you can try it. Whatever order you keep, you can get totally not reliable result. And another important thing is, or the most urgent thing is that why this method works. Well, when we are increasing the lambda, whether we will converge to the exact result or it will stabilize in a finite region. Well, actually, in our previous paper on matrix model bootstrap, we proved that the similar model in the large N1 matrix, it must converge. And recently, there is a mathematician told me that for this model, the toy model we just discussed, we can also prove that it converges. The essence of this proof is that we use some result from the Hamburger moment problem. Basically, what does this mean? This means that our positivity condition tells us that the integration is on the real line of the real axis. Let's put it more intuitively. Say, if you want to do a numerical integration in Mathematica, first you need to tell Mathematica what function you are doing the integration. Then you must tell Mathematica on which region you are doing the integration. So let's go back to our Schwinger-Dyson equation. For the Schwinger-Dyson equation, we are telling the bootstrap program what function we are doing the integration. And for the positivity condition, we are telling bootstrap on which kind of measure space we are doing the integration. That, by saying this, I mean that if we are integrating over some different region, let's say on the unit circle, complex unit circle, then this matrix will be very different. Actually, it is.
Sorry, could you maybe summarize here? So what precisely is what you are maximizing, and what are the constraints, just to be sure? So the constraint is this has to be positive, and you are maximizing?
Yes. The constraint is that this is an infinite dimensional matrix, right? You do some finite truncation, like let's say top 10 times top 10 matrix. And I remind you that this matrix, after you solve the Schwinger-Dyson equation, it is just a linear matrix on W2. This matrix is positive semi-definite. So you can minimize and maximize W2. This is a well-posed semi-definite programming. Okay, so the uniqueness or the generalization. My conjecture is that as long as you are in a finite number of integration, or you are integrating in a finite dimensional space, then this always leads you to a unique solution. This will always work because I tried it in, this is single variable integral. I tried it two variable integral or 3 variable integral. It always works. But there will be some tricky things happens when you have infinite number of degree of freedom. We all know that interesting physics phenomena. It will almost always happen when you have an infinite number of degree of freedom. So this can be tricky. In that situation, there might be some spontaneously breaking of symmetry. And the bootstrap program, it will tell you there will be multiple solutions, actually. So by this way, I'm saying that bootstrap, it is possible to capture the symmetry breaking. Okay, the last point, I want to discuss something about the symmetry assumption here. So if we don't assume the symmetry, that is, we don't assume the old moments they are 0, then what will we get? Well, we can solve from the Schwinger-Dyson equation that all the higher even moment, they are the linear function of W2, and all the higher odd moments, they are linear function of W1. And you do the maximization, you will get this result at lambda equals 10. So basically, bootstrap, if you don't assume the global symmetry, it will reconstruct the global symmetry. This is the conclusion. So this global symmetry assumption, it is not necessary, but it will make our algorithm more efficient. When we want to study the spontaneously breaking of the symmetry, well, we must don't assume the global symmetry, of course. And another thing I want to remark is that this symmetry actually makes the correlation matrix makes it block diagonal. We will see that by simply rearranging the indexes, we can make it to a even block and Z2 even block and Z2 odd block. The intermediate state, they are all odd moments, so they must be 0. So our original correlation matrix, it factorized to an even block and an odd block. What does this mean? Well, I will discuss later that when our global symmetry group is much more involved, that's not Z2, but some other finite group or other Lie group, then for each irreducible representation, we have a block. It can always factorize. Okay. The other model, here I won't go deep into it, but I'm presenting it because from studying of this model, the bootstrap result is much better than the current Monte Carlo implementation. So this is a large N2 matrix model. And this matrix, of course, it is already much more involved than our previous toy model. Here, our observables is not anymore some monomial in terms of X because of the A matrix and the B matrix, they are not commutative. So we have a series of this kind of observables. This is our observables. And for the equation, we also have the Schwinger-Dyson equation. The logic goes through very similarly, but there is some subtleties. I won't discuss it here. I will leave the subtleties when we are discussing the lattice gauge theory. I simply put the result. This is there are two parameters of the model, G and H. When we put G equals 1 and H equals 1, and we put lambda equals 11, what does this mean? This means that we set a length truncation on all of these observables. Let's say all the observables here means less than length 22. This is already a very high cutoff, you can see that. This is our result. The trace A square and the trace A to the fourth, they are very tightly bounded. This is a 6-dimensional result. And we can have the shrinking island for the trace A square and the trace A to the fourth. When we are increasing the lambda, that is, when we are considering length smaller than 14, 16, and this is 18, the island of the allowed region of trace A square and trace A to the fourth, this is trace A square, trace A to the fourth, it is shrinking very fast. And the lambda equals 10 and 11, they are on this very, very sharp cross here. So this is how we use the bootstrap method to do the so-called matrix bootstrap. This is some comparison with Monte Carlo study. Monte Carlo, someone did it using 800 times 800 Monte Carlo to get, it takes 80 to 85 hours to get 45 digits. But for the bootstrap, this is already old result. I notice you that we take 40 hours to get six digits. This is the result without some new implementation. With all this implementation, with all the implementation we develop later, I will describe in the lattice gauge theory. This should be less than 1 hour, I think. So this, you can see that this is very solid and promising numerical method. Okay, so finally we go to the lattice gauge theory. That is, here we are going to bootstrap the lattice gauge theory in the large N limit, that is planar limit, where all the dynamic forming will be suppressed and the only thing remaining is the gluon field, or our observable here, not like in the toy model, it is a monomial expectation, but here our observable is the Wilson loop. And here what we are going to bootstrap is the same as at the beginning of lattice QCD study. We are going to bootstrap this quantity, single black hat average. This is the result. Of course, I will come back to it later. And you can leave an impression of it. This is some upper bound and lower bound of the black hat average. And this red dot, or the purple dot here, this is a Monte Carlo study. And the perturbative line, this is a strong coupling and weak coupling expansion. This is 4D lattice gauge theory and 3D. Of course, they are all in the larger limit. Okay, let's start. The Schwinger-Dyson equation, or the equation of motion in this side, it is called the Marcinko-Migdal loop equation. It is a fully non-perturbative relation between the different Wilson loops. Here I will give some example. This is, to derive this equation, it is almost trivial, but a little bit tricky. It will be a little bit tricky. Due to the time reason, I will not derive it here. But I will show some example how this will work. Let's see, in the two-dimensional case, this is the linear variation. In this case, there is no nonlinear terms. This is fully linear. Put the simplest case, we have a black hat average, and we do the variation on this link, what we will get. This is the equation. So from up and down, we do the linear variation, so we will get, this is from, you are doing the variation downside, and you are doing the variation upside. So this is the loop equation for this kind of variation. What's more, we have the backtrack loop equation. You can see that this Wilson loop, there is a backtrack that going back and forth. If we are serious about it, this is exactly identical to the single black hat average. But when you are taking the Schwinger-Dyson variation, this is not. You can do the variation here from up and from down, you will get this equation. This term for the original Wilson loop, and there is an overlapping term. For the non-linear term, it cancels. So this is a linear equation actually. And even it is lambda independent. This equation doesn't contain lambda. So when does the nonlinear term appear? When you have overlapping terms. This is already a Wilson loop of length 8. So the nonlinear term appear much later than in the cutoff, in the length cutoff. So this is a variation correspond to the nonlinear term. So the nonlinear term here, you can use this variation to get that this is simply a minus of single black hat average square. Okay, this finish our very brief introduction to this Marcinko-Migdal loop equation. All these discussions, they are in the 2 dimension. In the 3 dimension or 4 dimension, well, except from the variation up and down, you have left and right. In the 4 dimension, you have another dimension, of course. This is a brief intuition of it. Okay, so what's the positivity condition? Here, because we are dealing with unitary matrix, so we must take the Hermitian conjugation instead of just take the original, like in the toy model, we take x squared. So, this is a path integral. It is integrating over SU infinity matrix, and this is a Wilson action. Sorry? Sum over all the black hat, including their orientations. All the black hats on the cubic lattice, actually. Okay, this is the positivity condition. Here, the Hermitian conjugation on Wilson path. By Wilson path, I mean that it is not a closed Wilson loop, but Wilson path has open indexes on both of its ends. So if we take the Hermitian conjugation of the Wilson path, we got the reverse of it. For example, we take this Wilson path, we got the, we take the Hermitian conjugation of this path, we got it reversed from this side. So for this matrix, we are taking 2 paths to construct the positivity matrix. So we will get on the diagonal, they are always 1, instead of, this is already very different from our toy model. And on the off-diagonal term, we have the single plaquette average. This matrix must be positive semi-definite, which means the conclusion is rather trivial, that our single plaquette must be smaller than 1. Generally, we can choose different starting point and end point of our matrix. For each starting point and end point, we have different matrices. So for convenience, we always put one of the end to 0, and the other end we can vary it. For example, if we put both of the end at 0, then we consider we set length truncation at 4. That is, we only consider the Wilson line at 4. We will get this big matrix. These are all open Wilson lines. These lines, they are the respective Hermitian conjugation of these Wilson lines. By doing the inner product, you can join them together. On the diagonal, they are always 1. And on the off-diagonal term, they can formulate a lot of, not really a lot of, but very big matrices of Wilson loops. Actually, there are six independent Wilson loops in this matrix, we will see. And why this is 8 Wilson line? Well, you see that we are, here I forgot to remind you that here we are dealing with in the 2-dimensional lattice gauge theory, but for higher dimension, this will be a trivial generalization. So there are 4 rotations to rotate the original Wilson loop here. And there is also a reverse of the path. That is, you can go this way, you can go this way or the reversed way. They are inequivalent Wilson lines, so there is 8 ones. So this is a 9 times 9 Wilson loop. The 1 here is a length 0 Wilson loop. Okay, and together with our original, the 2 McKinkle-McDowell loop equation we just listed, they are the only 2 non-trivial loop equations under a cutoff 8. So we have 6 variables, we have 2 equations. So effectively, we have 4 independent Wilson loops under the positivity condition of this big matrix. This is the semi-definite programming. So we can do the maximization and minimization. The lower bound, or the minimization, this is rather trivial. It's just 0. And the upper bound, this is smaller than 0.3 69300. This is a bootstrap result at lambda equals 1. So till now, we go exactly parallel to what we have constructed in the toy model, that single variable integral. But we may ask, how far can this method go? Actually, the method I discussed till now, it is basically in the pioneering work of Anderson and Kruczynski in 2007. This is basically their construction. But they found when they are going to higher order, they will meet with almost not possible to very large scale semi-definite programming. So they got very relatively very trivial result. So let's see how we can improve this method. First is the positivity condition. When we are discussing the toy model, we said that the positivity condition briefly capture on which measure space you are doing the integration. So we are switching to the measure space of large N lattice gauge theory. That is, on each lattice side, we have a SU infinity matrix. So we expect that we should have more positivity conditions than the original single variable integral. Actually, it is indeed. Our brief observation is that for that kind of positivity matrix, basically, if you can construct inner product on the space, all the subspace of operators, then you get a positivity matrix. So except the Hermitian conjugation, we have more well-known positivity conditions. That is the reflection positivity or the unitarity when you are talking about Minkowski field theory. That is, on the lattice, we have three kinds of reflection positivity conditions. Reflection by the side, that means reflection by the lattice line, and reflection by the middle of lattice line. This is independent reflection positivities, and also reflection by the diagonal. So these three kinds of reflection positivities, it turns out that they give independent positivity conditions on the older group of Wilson loops. For example, this is a 3D lattice Yang-Mills theory bootstrap result. The green line here, this is a bootstrap without reflection positivity when L max equals 12, so that we are bootstrapping all the Wilson lines with length less or equal to 12. And the orange line is when we consider the bootstrap, reflection positivity. So you see that it is indeed it is an independent set of positivity conditions. And this is this is not the end of the theory. When we are increasing the bootstrap cutoff, our positivity matrix, it actually grows exponentially. Let me give you a brief impression of how fast it grows. We already see that in the 2 dimension, when length L max equals 8, the matrix is 9 times 9. But in 3 dimension, when L max equals 16, the matrix is already 6,500 times 6,500. This is indeed, it is a super large scale semi-definite programming. Considering that, well, see, at this scale of large matrix, even you do the matrix multiplication, it is already very hard. So if you have a 4,000 times 4,000 matrix, you want to do the matrix multiplication. In our best implementation in the computer science, this will take you like 10 seconds CPU time already. So solving that kind of SDP is hopeless. So here we propose a symmetry reduction. That is, I described earlier, that actually our correlation matrix we just discussed, it can factorize to each irreducible representation of the global symmetry, and it can be block diagonal. By this way, we greatly simplify the problem. let's see. The correct intuition here is you can consider the partial wave expansion of the S matrix. From the partial wave expansion, you decompose the S matrix in different spin channels. And in different spin channels, the S matrix, they are orthogonal to each other. So it fully decomposes. Here, actually, this is mathematically guaranteed that as long as we have an inner product that preserves the global symmetry, it will decompose into different irreducible representation. Here, this is our global symmetry. For the S matrix, we have the SOD global symmetry. Here, we have the lattice. Somehow, it breaks the SOD global symmetry to the lattice point group. Together with Z2, this is actually the charge conjugation symmetry. So here, we list the symmetry group of different kind of inner product. So for the Hermitian conjugation, that is the positivity condition we initially proposed, this is a full group. B2, B3, and B4, here I denote the point group of the lattice. But when we are considering the reflection positivity, we can still do the symmetry reduction. But that symmetry group must stabilize the reflection plane. If it breaks the reflection plane, then it is not even a symmetry of the inner product. So this is our the method we propose. In the situation we just discussed, that is L max equals 8. We have I remind you we have 9 Wilson lines. They can fall into through some linear combination. They can fall into the different representations of our global group. Sorry, that is point group direct product with charge conjugation. We have, this is not, there are some representation, there is no vectors, but the vector in that representation only appear in higher length cutoff. Here we only have 6 irreducible representations, which means that our matrix will be a block diagonal by 6 matrix, each correspond to this matrix. Let's see. Because it is a 1 times man matrix, this is just linear equalities. So only in semi-definite programming, only in the semi-definite matrix is a singlet matrix or trivial representation. So by this way, we greatly reduce the 9 times 9 semi-definite programming to a series of linear inequality plus 2 times 2 times 2 matrix. So this greatly simplifies the problem. Actually, when you have, let's say, 1,000 times 1,000 matrix, this will speed up the program several order of magnitude. And what's more, we have the selection of multiplet. We already observed that, let's go back to our length 8 bootstrap. I notice you that in the 6 non-equivalent Wilson loops, the 2 times 2 big square Wilson loop doesn't even appear, which means that there are some multiplet that is not important. So we just discard it. After this symmetry reduction and after this selection of multiplet, the L3D L max equals 16, the huge matrix 6,500 times 6,500, it reduced to a 20 smaller matrix, each of very small size. This is our reduction to the positivity condition. What's more, we must do something to the loop equation. I already noticed you that the loop equation, when we are going to higher order, they are nonlinear. And I told you that the nonlinear equations, they are non-convex conditions. So when you are going to higher order, this is actually a non-convex optimization problem. It is not even FDP. So we must do some, actually this is called convex relaxation to make it into a convex situation. Well, how to do the convex relaxation? The most naive way is you just introduce new variables in the place of quadratic terms and totally forget that these quadratic terms, they are product of other Wilson loops. This is a this is already a relaxation. Of course, this must be correct, but you see, through this kind of relaxation, we must lose some information. Actually, we have a better choice. Let's see. Suppose we introduce 3 variables in terms of the x square, y square, and xy. We suppose xy, there are some very involved views and loops, and T1, T2, T3 is in the place of their product. Well, by this way, we substitute the T1, T2, T3 to the loop equations. The loop equations, they are linear, but these conditions, they are not linear. How to deal with it? Well, for the first one, x squared smaller than T1, we can relax it to x squared smaller or equal to T1. Or in the semi-definite matrix form, we can write it in this way. This is definitely a positive condition. This condition is a parabola, and this condition is a region inside the parabola. It is convex. And we can do the same thing on the y square, but we cannot reproduce the same story on the xy smaller than T3. How to do that? The reason we can't do it because this condition or this condition, they are not convex. Why? Because the true reason is that xy is not a positive definite quadratic term, quadratic form, but x squared it is. So the best we can do is that we take some linear combinations of x and y, and suppose that this relaxation is true for all the alphas. In fact, numerically, it is possible that we take a grid of alphas and we impose this relaxation condition on each grid, but we have better choice. I remind you that this is actually, in terms of alpha, this must be true for alpha. So this is a linear inequality. This must be true for any alpha. So the determinant of this inequality must be smaller or equal to 0. And we can massage this equation to get this condition. So combined with these positivity conditions, we finally reach that our final relaxation scheme, that we introduce T1, T2, T3 in the place of x squared, y squared, and xy. But the new variables, they must subject to this new positive semi-definite inequalities. This is our general scheme. Or when we have a more number of quantities, we have a much larger relaxation matrix. This is our convex relaxation of the loop equation. So, for example, in our problem, when L max equals 12, we have this kind of relaxation matrix. When L max equals 12, the Q which is the square of single plaquette average. It is the Orlean quadratic term in our loop equations. So this is the matrix, relaxation matrix. When we are going to higher cutoffs, the relaxation matrix will be bigger and bigger. Okay, so this is our final scheme. We take the minimization or maximization, the single plaquette average, subject to the relaxed Markinko-Migdal loop equation with the relaxation matrix and the correlation matrix in each irreducible block, and the reflection matrix in each irreducible block. And there is 3 kinds of reflection matrix. This is our final scheme. And we reach our final conclusion. This is a 2-dimensional large N Yang-Mills theory. In this case, this is actually a solvable model. We have the exact solution for the UP in the weak coupling region and strong coupling region. We see that for the yellow region, this is L max equals 8. We have already reproduced. And the orange region is L max equals 12. The blue region is L max equals 16. So when we are increasing the bootstrap cutoff, except from the critical value, in the neighborhood of critical value, the bootstrap doesn't perform as good as other regions, but we see that it is shrinking very fast. And this is the 3D and 4D result. This is what we already presented. We see that in the weak coupling region, for the lattice Yang-Mills theory, weak coupling region is a correct regime when you are doing the renormalization flow to study QCD. This is a physically critical region. And we see that in this region, we are already extremely close to the Monte Carlo region. Actually, in the asymptotic region, that is lambda is very close to 0. We are already better than the Monte Carlo in the upper bound. And for the lower bound, it converges to the exact value much slower. The correct intuition for it is that in this allowed region, our best estimate for the exact value, it should minimize the action. But the action is the minus of plaquette average. So the exact value should be very close to the upper bound of the bootstrap result. So this is the intuition. But for the strong coupling region, that is Wilson action is greatly suppressed due to that lambda become large. So the upper bound and lower bound, when lambda goes large, they are equally close to the exact result. Okay, this is the main result of our bootstrap. Here are some final remarks. So here, the Marcinko-Migdal loop equation, actually they are overdetermined. That by this I mean there are some linear redundancies. I mean some loop equations, they are linear combination of other loop equations. So solving this kind of loop equations, they might be very challenging. There might be some numerical instability. We hope that in the near future there will be some mathematical theorem that help us to get rid of these linear redundancies. And we notice that the number of independent Wilson loops, they are much larger than the number of independent loop equations. That means if we introduce one new loop equations, maybe we introduce like 6 or 8 new Wilson loops. But the new variables, they are subjected to the positivity conditions. So actually our result shows that this is worth it. And another remark is that all the Wilson loop average, they are real values. This is just from the global symmetry. We assume that the charge conjugation global symmetry, so that all the Wilson loop, they are real. If we don't assume it, by this we mean that we want to bootstrap the spontaneously breaking of charge conjugation, then this will be much more involved. This will be a Hermitian semi-definite programming. It is much more involved, actually. Okay, this I already said. And the next point is that this is very perfectible. All our code, basically, it is single core. We just run it. There is most part of our algorithm, there is no parallelization. So we expect a much better result when we parallelize it and we go to Lmax equals 24. We think at this order of magnitude, we should, for the single plaquette average, we should already get better result than the Monte Carlo. And this method is not limited to large N. Actually, all this method, it could be generalized straightforwardly to the N equals 3, which is of physical importance here. And another thing is that we can not only bootstrap the single plaquette average, we can get estimate on all the family of these Wilson loops under our bootstrap cutoff. Let's see, our bootstrap cutoff is 16, so we can get estimate of all Wilson loops under the length cutoff 16. So SDP solver. SDP is a very mature industrial problem, and they are this is one of the commercial solver of it. This is Mosaic. It take our workstation 20 hours CPU time for a single point in the 4-dimensional case. Okay, the final remark is that we are not far from the real physics. Thanks. Yes.
Can you recover 11/3 from your computations?
Sorry?
Can you compute the beta function?
Beta function. Beta function, it is not relevant in here because here we are just computing the expectations of the Wilson loops, and computing beta function, it should be there is already very mature method in the continuous QCD. So in this case, I don't think there is any construction to formulate the beta function in terms of the Wilson loop expectations, right? And on the lattice, most of the time we are not interested in the beta function. We are using some systematic way to extract the physics quantities directly from the lattice simulation. Or the beta function or the physical scale, it is directly related with the lambda here. In the small lambda limit, that is when your lambda goes to 0, this corresponds actually to the QCD in the continuum.
More questions?
Yes?
So that was n in your calculation, the n of SUN, and is
yes,
that
n is the number of colors.
Yeah, sure, but where did it appear in your calculation? And is there any simplification for n equals infinity or no?
Sorry, where do you mean?
Large n. Is there any simplification for large n in your approach?
A large n. Yes, we are always working the large n limit.
Always. But you said you can do also n equals 3 or?
Yes. For n equals 3, there is no large n factorization. So you not only need to write down the loop equation for single trace variables, but also loop equations for multi-trace variables. So this is the story. This will be generalized very straightforwardly. But for n equals 3, the fermion side, it is not suppressed. Rigorously speaking, you must take fermion into account. This is already very challenging in the lattice QCD side, taking into account of the dynamical fermion.
So it seems that the Migdal-Makeenko equations are not more complicated if you write them for, say, big rectangular loop, Wilson loop. So maybe you are able to solve the problem for the quark-antiquark potential in this way. Indeed, the symmetry of the Wilson loop, the rectangular Wilson loop, is a bit smaller than the symmetry you use when calculating the plaquette average, but still maybe it's still possible.
Sorry, could you repeat your question?
Oh, I mean, have you thought of computing the Wilson loop?
The other Wilson loops.
Sorry?
You mean, have you ever thought of computing other Wilson loops?
Oh, yes, computing rectangular Wilson loop.
Yes, I gave a remark here that if our bootstrap cutoff is high enough, in principle, we can compute all the large Wilson loops.
I think that you don't need to make it as big as the size of the loop, because they will close in...
yes, you mean start the bootstrap program from some big...
Exactly.
Yes, that's possible. But by this way, I think you can only compute some ratios of Wilson loops, because here you set the normalization of vanishing Wilson loop, that is length 0 Wilson loop to 1. But for a big square, you can only compute their ratios, setting some normalization. I thought about it, but it seems a bit involved. I didn't do it seriously, I must admit.
You can compare Wilson loops with different sizes and take the ratio. I mean, if you compare Wilson loop with different aspect ratios,
yes,
then you don't need really the normalization. Yes.
Yeah, that's true. That's true. Yeah, it is possible. But apparently, there must be a lot of effort to do such a bootstrap program.
Yes, you will have less symmetry. And another thing, maybe you are able to investigate gauge theory with infinite temperature, with the periodic time direction on the lattice.
Yes, this we already put it on the infinite lattice. So on the infinite temperature, I think you are compactifying it as just a plane, right?
Yeah, it's very simple. Yes, just you change the weights of your ensemble of loops.
Yeah, of course, I think it's possible. Even you can bootstrap the finite temperature QCD. You select the direction and you compactify it.
Actually, you will have a bit more loops because you will have loops that go around.
Yes, that's the Polyakov loop. Yes, indeed. So you can study in principle, you can study the confinement of the QCD. Yes.
Thanks.
Volodya?
Just a little comment to clarify maybe your discussion that in this method, say in Monte Carlo, you can choose your favorite loop and compute it by Monte Carlo. And it will be one single calculation for, of course, their infrared cutoff would be the size of the lattice. Yes, here we don't have, the lattice is infinite, but we have finite length of the loops. But in our method, we have to calculate all loops up to a given one. So you cannot start from very big loop and write a few equations and pretend that you get anything. You have really to get all loops from plaquette, single plaquette, up to the loop of your size. Yes, yeah. Well, at least if you propose something else, maybe, but I don't see how you can start from very big loop. So you change the shape of the loop, applying equations little by little, but you don't know what what is in the middle. But the advantage of this method is that for these small loops, you really do very precise calculations. But the disadvantage is that you cannot start from very big loop, including finite temperature. If you are on the cylinder should be of the length like 3, 4, not more. That's the state of things. If you have other ideas, I would be happy to discuss. Maybe if you combine it with summary normalization scheme, maybe you're right, but it's just to... Yes, yes. But what is nice about this method, you get really precise inequalities on all these loops. They are rigorous, but with all these normalizations, you lose a little bit control on it.
Let me comment a little bit. Actually, starting from a big Wilson loop, I thought about it. My conclusion is that this might be possible, but technically it will be very hard. Maybe we need some new ideas to see how to bootstrap this very big Wilson loops, or start the bootstrap program from the Wilson loops. On the current setting, this is very far, actually. But if we have some new ideas, who knows? Yeah, in principle, it is possible, I think.
Okay, further questions? Okay, let's thank again the speaker.
Okay. Thanks.